Okay, esoteric dubitism here again. Welcome. Appreciate everyone who's been giving me some feedback. As I said, this one is meant as directly a form of just a public study session. I'm not sure what's going to go from this, so I wanted to start by, I've had this on my desk for a while, by reading at least parts of Stephen Grossberg's theory of adaptive resonance theory on the brain in 2016, and try to get this modern evidence of consciousness arising from the brain, which obviously I'm not in agreement with, but I want to see the current state of the evidence, the current state of the research, and because this is already a little more than a year ago, so it's pretty recent. And blessing. So this is a pretty long article, and a lot of it's pretty technical, so I'll probably just read parts of it. And then I have some finishing slides on deconstructionism, linguistics that I thought I'd go through, and that's the conclusion of this series that I've been doing. Plus I have my slides on the history of Christian theology, and then maybe I'll even do some Judaic stuff on the soul, but I'll probably do that separately. So just make sure this is working, and then I'm going to start this article. Okay, so let's get started. Stephen Grossberg, towards solving the hard problem of consciousness, the varieties of brain resonances, and the conscious experiences that they support. The hard problem of consciousness is the problem of explaining how we experience qualia or phenomenal experience, such as seeing, hearing, and feeling, and knowing what they are. To solve this problem, theory of consciousness needs to link the brain to mind by modeling how emergent properties of several brain mechanisms interacting together embody detailed properties of individual conscious psychological experiences. This article summarizes evidence that adaptive resonance theory, or ART, accomplishes this goal. So adaptive resonance theory is a cognitive and neural theory of how advanced brains autonomously learn to attend, recognize, and predict objects and events in a changing world. ART has predicted that all conscious states are resonant states. As part of its specification of mechanistic links between processes of consciousness, learning, expectations, attention, resonance, and synchrony, it hereby provides functional and mechanistic explanations of data ranging from individual spikes and their synchronization to the dynamics of conscious perpetual cognitive and cognitive emotional experiences. ART has reached sufficient maturity to begin classifying the brain resonances that support conscious experience of seeing, hearing, feeling, and knowing. Psychological neurobiological data in both normal individuals and clinical patients are clarified by this classification. This analysis also explains why not all resonances have become conscious and why not all brain dynamics are resonant. The global organization of the brain into computationally complementary cortical processing streams and the organization of the cerebral cortex into characteristic layers of cells figure prominently in these explanations of consciousness and unconscious processes. Alternative models of consciousness are also discussed. So towards solving the hard problem of consciousness, we've discussed this at length. What is the hard problem of consciousness? David Chalmers. The really hard problem of consciousness is a problem of experience. When we think and perceive, there is a roar of information processing, but there is also a subjective aspect. Nagel has put it, there is something it is like to be a conscious organism. The subjective aspect is experience. When we see, for example, we experience visual sensations, the felt quality of redness, the experience of dark and light, the quality of depth in a visual field. Other experiences go along with perception in different modalities, the sound of a clarinet, the smell of mothballs. There are bodily sensations from pains to orgasms, mental images that are conjured up internally, the felt quality of emotion, and the experience of streams of conscious thought. What unites all of these states is that there is something it is like to be in them. All of them are states of experience. Internet Encyclopedia of Philosophy goes on to say the hard problem of consciousness is the problem of explaining why any physical state is conscious rather than non-conscious, is the problem of explaining why there is something it is like for a subject in conscious experience, why conscious mental states light up and directly appear to the subject. The usual method of science involves explanation of functional, dynamic, and structural properties, explanations of what things do, how it changes over time, and how it is put together. But even after we have explained the functional, dynamic, and structural properties of the conscious mind, we can still meaningfully ask the question, why is it conscious? This suggests that an explanation of consciousness will have to go beyond the usual methods of science. Consciousness therefore presents a hard problem for science, or perhaps it will mark the limits of what science can explain. Explaining why consciousness occurs at all can be contrasted with so-called easy problems of consciousness, the problem of explaining the function, dynamics, and structure of consciousness. These features can be explained using the usual methods of science, but that leaves the question of why there is something it is like for the subject when these functions, dynamics, and structures are present. This is the hard problem. There seems to be an unbridgeable explanatory gap between the physical world and consciousness. All these factors make the problem hard. Philosophical opinions about the hard problem are so diverse and strongly felt that by their supporters that even after attempting a possible scientific approach to solving the hard problem may sometimes feel like stepping on a philosophical third rail. This is because philosophers vary passionately in their views between the claim that there is no hard problem remains once it is explained how the brain generates experience, as in the writings of Daniel Dennett, to the claim that it cannot in principle be solved by the scientific method, as in the writings of David Chalmers. To what extent can a scientific theory clarify the hard problem? The present article presents a theory that proposes answers, however incomplete, that respond to various of these philosophical concerns by showing how this theory scientifically clarifies various of the distinctions that philosophers have discussed. Looking ahead, then we note the following. First, it's fair to ask what kind of event occurs in the brain during a conscious experience that is anything more than just a whirl of information processing. What happens when conscious mental states light up and directly appear to the subject? This article proposes that over and above just information processing, our brains sometimes go into a context-sensitive resonant state that can involve multiple brain regions. This article summarizes some of the abundant experimental evidence that all conscious states are resonant states. Not all brain dynamics are resonant, and thus consciousness is not just a whirl of information processing. Second, it is fair to ask, when does a resonant state embody a conscious experience? Why is it conscious? And how do different resonant states support different kinds of conscious qualia? The other side of the coin is equally important. When does a resonant state fail to embody a conscious experience? In order to provide even partial answers to these questions, the theory will be used to explain how various evolutionary challenges that advanced brains face in order to adapt to changing environments in real time have been met with particular conscious states, and how these conscious states form part of the larger adaptive behavioral capacities. In this regard, the theory argues that humans are not conscious just to platonically contemplate the beauty of the world. Humans are conscious in order to enable them to better adapt to the world's changing demands. To illustrate these claims, the theory proposes how the brain generates resonance that supports particular conscious experience of seeing, hearing, feeling, and knowing. In doing so, it suggests how resonance for consciousness seeing help to ensure effective reaching, resonance for consciousness hearing help to ensure effective speaking, and resonance for conscious feeling help to ensure effective goal-directed action. The theory also proposes why different resonances are triggered at the processing stages that they are, and suggests how several functionally different kinds of resonance can interact with one another so that we can consciously see a familiar valued object. We can also know some things about it and have appropriate feelings that are directed towards it. Towards this end, the article will summarize and explain 6 different types of neural representations of conscious qualia, and will provide enough theoretical background and data explanations based on these representations to illustrate their explanatory and predictive power. The theory's explanation and predictions, many of them stated in this article for the first time, also shed further light on the issues by suggesting multiple kinds of experiments to deepen our mechanistic understanding of the brain, mechanisms for generating conscious resonances. So the 6 type of resonance mentioned by this article: surface shroud, feature category, stream shroud, spectral pitch and timbre, item list, cognitive emotional. The surface shroud allows people to see visual objects or seen. Feature category, recognize visual objects or seen. Stream cloud, hear auditory object or stream. Spectral pitch and timbre, recognize auditory object or stream. Item list, recognize speech and language. Cognitive emotional, feel emotion and know its source. Establishing a linking hypothesis between resonant brain dynamics and the conscious mind. Before presenting this theory, it is important to ask how far can any scientific theory go towards achieving this goal. Let us suppose that a theory exists whose neural mechanisms interact to generate dynamic states with properties that mimic the parametric properties of the individual qualia that we have consciously experienced, notably the spatial temporal patterning and dynamics of the resonant neural representations that represent these qualia. Suppose that these resonant dynamic states, in addition to mirroring properties of subjective reports of these qualia, generate observable data about these experiences that are collected in psychological and non-invasive neurobiological experiments on humans and are consistent with psychological, multi-electrode, neurophysiological data and other types of neurobiological data that are collected from monkeys who experience the same stimulus condition. Given such detailed correspondence with experience qualia and multiple types of data, it can be argued that these data dynamically resonant states are not just neural correlates of consciousness, rather they're mechanistic representations of the quality that embody individual conscious experience on the physiological level. If such a correspondence between detailed brain representations and detailed properties of conscious qualia occurs for a sufficiently large body of physiological data, then it would provide strong evidence that these brain representations create and support these conscious experiences. A theory of this kind would have provided a linking hypothesis between brain dynamics and the conscious mind. Such a linking hypothesis between brain and mind must be demonstrated before one can claim to have a theory of consciousness. If, despite such a linking hypothesis, a philosopher or scientist claims that unless one can see red or feel fear in a theory of the hard problem, then it does not contribute to solving that problem, that no scientific theory can ever hope to solve the hard problem. This is true because science, and we know it cannot do more than to provide a mechanistic theoretical description of the dynamic events that occur when individual conscious qualia are experienced. However, as such principle, albeit incrementally developing theory of conscious becomes available, including increasingly detailed psychological, neurobiological, and even biochemical processes in its explanations, it can dramatically shift the focus of discussion about consciousness, just as relative theory transformed discussions of space and time, the quantum theory, and how matter works. As in quantum theory, there are measurement limitations in understanding our brains. We can no more personally ride an electron than we can enter a neuron that is participating in a conscious experience. Such an empathetic limitation has not deterred physicists from believing that they have acquired an effective understanding of the physical world based on their ability to explain and predict enough facts about it. This article subscribes to the view that it will no longer deter psychologists and neurobiologists from believing that they have acquired an effective understanding of the hard problem based on their own explanatory and predictive successes. So adaptive resonance theory links resonant dynamics and the conscious mind. To this end, the current article summarizes a theory called adaptive resonance theory that explains neural mechanisms and psychological function of dynamic brain states whose properties mimic subjective properties of individual conscious experiences, and as they explain parametric properties of many physiological data about these experiences, including their spatial temporal dynamics. Art also proposes in what brain region these dynamical states may occur, and how these dynamical states may all arise from a unified set of shared neural mechanisms, even when they carry out different functional roles and adaptive behaviors using different parts of the brain. Such a dynamic state is called adaptive resonance. As explained in greater detail in subsequent sections, a resonance in a dynamic state during which neuronal firings occur across a brain network are amplified and synchronized when they interact via reciprocal excitatory feedback signals during a matching process that occurs between bottom-up and top-down pathways. Often the activities of these synchronized cells oscillate in phase with one another. Resonating cells activities also focus attention upon a subset of cells, thereby clarifying how the brain can become conscious of attended events. It is called adaptive resonance because the resonant state can be trigger learning within the adaptive weights or long-term memory traces that even at the synapses of these pathways. Adaptive resonance theory explains how an adaptive resonance, when it occurs in different specialized anatomies, that receive different types of environmental and brain inputs can give rise to different conscious qualia as emergent or interactive properties of specialized networks of neurons. In particular, art proposes how brain resonance mirrors parametric properties, a conscious experience of seeing, hearing, and feeling, and knowing what these experiences are. Not all cells that sustain adaptive resonance may represent conscious contents of an experience. Art explains why only cells that are sensitive to these kinds of physiological, psychological discriminations that are embodied within the conscious experience can do this, and why these discriminations can occur only at the prescribed stages of brain processing. Neurophysiological data about perceptual experiences like binocular rivalry illustrate this fact, and neural networks have explained and indeed predicted key properties of this data. In this regard, art predicts that all conscious states are resonant states, but the converse statement that all resonant states are conscious states is not true. If in fact the concept of resonance is more general than that of consciousness, then such a theory needs to explain why that is so and how conscious states arise from the more general function. Brain dynamics can also occur that do not include any possibility of resonance, notably during the generation of spatial and modal representations, and thus may not support any conscious experience. Current article proposes answers to these questions, in addition by explaining neural mechanisms and psychological functions of adapted resonances and specifying the functional, anatomical, and neurophysiological differences between resonance that can support conscious experience of seeing, hearing, feeling, and knowing. Art provides, as noted above, a guide to how many different kinds of future experiments may be designed to provide more information about the brain resonances that support conscious experiences of qualia. Before explaining how art can clarify the brain substrates of conscious experiences, it's useful to realize that art was not developed to explain consciousness. Rather, it was developed to explain and predict large psychological and neurobiological databases about learning, perception, cognition, and emotion in order to achieve a self-contained exposition, notably to enable new data explanations and predictions to be understood about art. It is thereby necessary to review aspects of how art explains data, whose properties naturally lead to neural representations of conscious qualia. It also needs to be emphasized that the current article explains much more data about consciousness than has previously been done using art or any other theory. It extends art rather than just reviewing it. The article also unifies parallel streams of modeling activity that have been separately developed, but whose synthesis is needed to draw many of the article's conclusions about consciousness. Key properties of these separate modeling streams thus need to be reviewed so that their synthesis can be described in a self-contained way. This synthesis and extension of art model is called conscious art, or C-art model, to distinguish from its precursors. Even if one's personal definition of the hard problem excludes any scientific theory, or if one is not interested in the hard problem, one could benefit from how the current C-art theory explains the functional meaning of many different kinds of psychological and neurobiological data, both normal and clinical, that no other theory has yet explained, and makes predictions to further these explanations. So the stability-plasticity dilemma and rapid learning throughout life. Humans are able to rapidly learn enormous amounts of new information on their own throughout life and integrate all this information into unified conscious experience that coherent a sense of self. One is only to see an exciting movie or just once to marvel at the capacity, since we can describe many details about it later on, including consciously experience moments of seeing, hearing, feeling, and knowing, even though the individual scenes flowed by quickly. Humans can rapidly learn new facts without being forced to just as rapidly forget what they already know, even if no one tells us how the rules of each environment differ or change through time. When such forgetting does occur, it often is called catastrophic forgetting. So Grossberg, 1980, called the problem whereby the brain learns quickly and stably without catastrophically forgetting its past knowledge the stability-plasticity dilemma. Art was introduced to explain how brains solve the stability-plasticity dilemma. Since its introduction in 1976, art has been incrementally developed into cognitive and neural theory of how the brain autonomously learns to attend, recognize, and predict objects and events in the changing world without experiencing catastrophic forgetting. Art currently has the broadest explanatory predictive range of available cognitive and neural theories. How does consciousness enter the art story? To solve the stability-plasticity dilemma, art specified mechanistic links between brain processes of learning, expectations, attention, resonance, and synchrony to explain psychological data about seeing, hearing, feeling, and knowing. As these discoveries were made, it became clear that the resonance hereby discovered also exhibited parametrical properties of individual conscious experience embodied with the spatial temporal patterning of cell activities across networks of featured detectors. Indeed, early mathematical results about brain functional units of short-term memory and long-term memory proved that the functional units of both short-term and long-term memory are distributed patterns across networks of feature-selective cells. The later results showed how these distributed patterns form part of a synchronous resonant states that focus attention upon the critical features that represent predictive neural information, including those feature patterns that embody the parametric properties of individual conscious experience. Is such discoveries repeated multiple times over a period of decades led to growing understanding of links between process of consciousness, learning, expectation, attention, resonance, and synchrony. These processes are called the clear processes. Art predicts that all brain representations that solve the stability-plasticity dilemma use varieties of Clear's mechanisms. The Clear's mechanism clarify what many animals are intentional beings, why many animals are intentional beings who pay attention to salient objects, why all conscious states are resonant states, and how brains can learn both many-to-one maps representations whereby many object view positions and sizes all activate the same invariant object category, and one-to-many maps representations that enable us to expertly know many things about individual objects and events. So art accomplishes these properties by proposing how top-down expectations focus attention on salient combinations of cues called critical feature patterns, characterizes how attention may operate via form of self-normalizing bias competition, and explains how top-down attention matching may help solve the stability-plasticity dilemma. In particular, when good enough match occurs between a bottom-up input pattern and a top-down expectation, the synchronous resonant state emerges that embodies an attentional focus. Such a resonance is capable of driving fast learning that incorporates the intended critical feature pattern into both the bottom-up adaptive filters that activate recognition categories and the top-down expectation that are read out by them, hence the name adaptive resonance, while suppressing unattended outliers that could have caused catastrophic forgetting. Processes that are summarized by the Clear's mnemonic are related to one another in specific ways that psychological and neurobiological data have supported. For example, attention and learning are linked in a manner consistent with our predictions about visual perceptual learning and auditory learning and somosensory learning. Art predicts links between attention and synchronous oscillations that were subsequently experimentally reported, and between synchronous oscillations and consciousness. Although several distinguished neurophysiologists have proposed a linkage between synchronous oscillations and consciousness without a detailed computation theory to link mechanistic properties of resonant brain states to parametrical properties of individual conscious physiological experience, and an explanation of where and why particular kinds of resonance occur in the brain to support different subjective experiences, this proposal does not rise to the level of a true theory of conscious awareness. Section 20 provides a comparative discussion of several approaches to explaining consciousness. In the discussion below, link between attention and consciousness play an important role and include several functionally different kinds of attention, such as prototype attention during recognition learning, as well as boundary attention and surface attention during visual perception. Some authors have nonetheless argued that visual attention and consciousness can be disassociated. 2007 study note that subjects can attend to a location for many seconds and yet fail to see one or more attributes of an object of that location. In lateral masking, visual crowding, the orientation of a peripherally presented grading is hidden from conscious sight, but remains sufficiently potent to induce an oriented dependent after effect. In fact, the study described can be explained by how art links attention and consciousness, notably by using properties of a surface shroud resonance. Properties of consciousness, visual crowding experience follow immediately from properties of the surface shroud resonance that are formed in response to visual crowding stimuli, as explained in section 10. So since art was introduced in 1976, it has undergone continual development to explain and predict increasingly large behavioral and neurobiological databases, ranging from normal and abnormal aspects of human and animal perception and cognition to the spiking and oscillatory dynamics of hierarchical, organized, laminal, thalamocortical, and corticortical networks and multiple modalities. Indeed, some art models individually explain, stimulate, and predict behavioral, atomically, neurophysiological, biophysical, and even biochemical data. Art currently provides functional mechanistic explanations of data concerning such diverse topics as laminar cortical circularity, invariant object and scenic gist learning and recognition prototype, surface and boundary attention, gamma and beta oscillations, learning of entorhinal grid cells and hippocampal place cells, computation of homologous spatial and temporal mechanisms in the entorhinal and hippocampal systems, vigilance breakdowns during autism, and medial temporal amnesia, cognitive emotional interaction that focus attention on valued objects in an adaptively timed way, item order, rank working memories, and just learn list chunks for the planning of controlled sequence of linguistic, spatial, or modal information. Conscious speech percepts that are influenced by future context, auditory streaming and noise during such segregation, and speaker normalization, brain regions whose function is clarified by art include visual and auditory neocortex, specific and non-specific thalamic nuclei, intertemporal, parietal, prefrontal, etnorhinal, hippocampal, parahippocampal, pararhinal, and motor cortices, frontal eye fields, supplementary eye fields, amygdala, basal ganglia, cerebellum, and superior cochleus. These unified explanations of many different types of data increase confidence in the emerging classifications of resonances. The article first describes resonance that support visual seeing, knowing, and reaching, then auditory hearing and speaking, and finally emotional feeling, knowing, and acting, while also proposing how these various kinds of resonance may interact together. A comparative discussion of some other prominent contributions to conscious studies is then provided, followed by concluding remarks. Much of this text tries to explain how key design principles and neural mechanisms control the brain's processing of visual, auditory, cognitive, and affective signals. This includes a frontal attack on how the brain learns to attend, recognize, and predict such events, as noted above. How such a capability works involves linked processes of consciousness, learning, expectations, attention, resonance, and synchronony in each of these domains. The text also explains what the visual, auditory, cognitive, and affective representations and that emerge from these processes, because if one does not understand a lot about how visual, audition, effect, and recognition actually work, then one cannot say anything deep about how, when, and why their representations of individual experiences become conscious. Along the way, the text proposes explanations of how and why the resonance that involve these processes embody the subjective properties of conscious quality, not just correlate with them, including how and why these resonances occur at the processing stages they do. So equations, modules, and modal architectures. Before describing how these resonances work, it is helpful to review the kind of mind-brain theory that enable links between brain mechanisms and psychological functions to be established, and how similar organizational principles and mechanisms suitably specialized can support conscious quality across modalities. One reason for this intermodality unity is that a smaller number of equations suffice to model all modalities. These include equations for short-term memory, long-term memory, medium-term memory that were introduced by Grossberg going back to 1968. These equations are used to define a somewhat larger number of modules and microcircuits that are also used in multiple modalities where they can carry out different functions within each modality. These modules include shunting on-center, off-surround networks, gated dipole opponent processing networks, associative learning networks, spectral adaptive time learning networks, and the like. Each of these types of modules exhibit a rich but not universal set of useful computational properties. For example, shunting on-center off-surrounded networks can carry out properties like contrast normalizing, including discounting the illuminant, contrast enhancements, noise suppression, winner-take-all choice. short-term memory and working memory storage, attentive matching of bottom-up input patterns and top-down learned expectations, and synchronous oscillations and traveling waves. These equations and modules are specialized and assembled into modal architectures, where modal stands for different modalities of biological intelligence, including architectures of vision, audition, cognition, cognitive emotional interactions, and sensory motor control. An integrated self is possible because it builds on a shared set of equations and modules within modal architectures that can interact seamlessly together. Modal architectures are general purpose in that they process any kind of inputs to that modality, whether from the external world or from the modal architectures. They're also self-organizing in that they can autonomously develop and learn in response to these inputs. Modal architectures are thus less general than the von Neumann architecture that provides the mathematical foundation of modern computers, but much more general than the traditional AI algorithm. Art networks form part of several different modal architectures, including modal architectures that enable seeing, hearing, feeling, and knowing. So complementary processing streams for perception, cognition, and space action. How are modal architectures organized with respect to one another? This is a question about the global organization of the brain and mind. Modal architectures illustrate at least two general computational paradigms. The first paradigm is called complementary computing. Complementary computing describes how the brain is organized into complementary parallel processing streams whose interactions generate biologically intelligent behaviors. A single cortical processing stream can individually compute some portion properties well, but cannot by itself process other computationally complementary properties. Pairs of complementary cortical processing streams interact using multiple processing stages to generate emergent properties that overcome their complementary deficiencies to compute complete information to represent or control some faculty of intelligent behavior. You see in the chart some complementary processes: visual boundary, visual surface, motion, the stream perception recognition, space and action, object tracking, optic flow navigation, motor target position, volitional speed, and the different part of the brains where they occur. For example, the category of learning, attention, recognition, and prediction circuits of art are part of the ventral or what cortical processing stream for perception and cognition. The ventral stream exhibits properties that are often computationally complementary to those of the dorsal or where and how cortical processing stream for spatial representation and action. One reason for this what-where complementary is that the what stream learns object recognition categories that are substantially invariant under changes in object's view, size, and position. These invariant object categories enable our brains to recognize value objects without experiencing a combinatorial explosion. They cannot, however, locate and act upon the desired object in space, where stream spatial and motor representations can locate objects and trigger actions toward them, but cannot recognize them. By interacting together, the what and where streams can recognize value objects and direct appropriate goal-oriented action towards them. Table 4 summarizes basic complementary properties of the what and where cortical streams. As will be discussed in greater detail below, perceptual cognitive processes in the what stream often use art-like excitatory matching and match-based learning to create self-stabilizing categorical representations of objects and events that solve the stability-plasticity dilemma. They thereby enable increasing expertise and ever-expanding sense of self to emerge throughout life. As further discussed, Section 7, excitatory matching by the art matching rule enable us to prime our expectations to anticipate objects and events before they occur, and to focus attention upon expected objects and events when they do not occur. No less important is the fact that good enough matches between expected and actual events trigger resonant states that can support learning of new recognition categories and refinement of old ones, while also triggering conscious recognition of the critical feature patterns that are attended as part of these precepts. Excitatory matching also controls reset of the attention focus when bottom-up inputs significantly mismatch currently active top-down expectations. As will be described below in greater detail, cycles of resonance and reset underlie much of the brain's perceptual and cognitive learning dynamics. So here we see the what and where. matching and learning categories. Complementary spatial motor processes in the where stream often use inhibitory matching or mismatch-based learning to continue to update spatial maps and sensory motor gains that can effectively control our changing bodies throughout life. As discussed in section 14.3, inhibitory matching can take place between representations of where we want to move and where we are now, so that when we arrive at where we want to be, the match equals 0. Inhibitory matching in the vector associative map, or VAM, matching rule thus cannot solve the stability-plasticity dilemma. Instead, spatial maps and motor gains experience catastrophic forgetting as they learn how to accurately control our changing bodies throughout life. Together, these complementary processes create a self-stabilizing perceptual cognitive front end in the what stream for learning about the world and becoming conscious of it, while it intelligently commands more label spatial motor processes in the where stream than control our changing bodies. Thus, if only due to complementary organization of the brain, art is not a theory of everything. Likewise, because excitatory matching is needed to generate resonance that support conscious internal representations, spatial and motor processes, procedural memories that use inhibitory matches cannot generate conscious internal representations. So laminar neocortical circuits to represent higher order biological intelligence. The second computational paradigm is called laminar computing. Laminar computing describes how the cerebral cortex is organized into layered circuits whose specializations support all higher order biological intelligence. Indeed, the laminar circuits of cerebral cortex seem to realize a revolutionary computational synthesis of the best properties of feed-forward and feedback processing, digital and analogic processing, and data-driven bottom-up processing, and hypothesis-driven top-down processing. ART mechanisms have to the present been naturally embodied in laminar cortical models of vision, speech, and cognition, specifically the 3D laminar model of 3D vision and figure ground separation, the Cartword model of speech perception, and the list parse model of cognitive working memory and chunking. Each model uses variations of the same canonical laminar cortical circuitry, thereby providing additional insights on how specialized resonants use similar types of circuits to support different conscious experience. So an example of complementary computing, visual boundaries, and surfaces. In order to understand how surface shroud resonance can support conscious seeing of visual qualia, it is necessary to summarize basic cortical processes whereby the brain sees. These explanations will clarify why surface shroud resonance are predicted to be triggered by interactions between prestriate visual cortical area V4 and the posterior parietal cortex. Okay, I'm going to skip through quite a bit because this is quite a lot here. Perhaps the most basic fact about 3D vision and figure ground perception is that its functional units are 3D boundaries and surfaces. Where these words need to be properly understood, these processes were first modeled by Grossberg in 1984 and have provided a foundation for subsequent explanations and predictions about many data, including how looking at 2D pictures can generate conscious 3D precepts of occluding and occluded objects. Visual boundaries and surfaces are computed by the blob and interblob cortical processing streams that occur within and between the cortical areas V1, 2, and 4, and provide a vivid example of complementary computing. Visual illusion of neon color spreading dramatically illustrates the complementary properties of how boundaries are completed and surface brightness and colors are filled in. So neon color spreading gaps and ends. Just an example. Encourage people to read through this. Simple cells and hierarchical resolution of uncertainty. Why does the brain compute ends, cuts, and gaps? Surely not just to cause a visual illusion like neon color spreading. In fact, spatial and orientation competition are needed to achieve effective vision for the following reasons. An early stage of boundary processing uses contrast-sensitive cells with orientational tuned receptive fields that begin to estimate boundary orientations at each position. These orientally tuned simple cells can respond to oriented distributions of contrast in response to scenic lines, edges, textures, and shading, not just edges alone. If our brain did not use specialized detectors like edge detectors, then it would require many different types of specialized detectors, followed by complicated subsequent processing to try to fuse together all their information. Such an endeavor would fail, if only because in many natural scenes, lines, edges, textures, and shading are all overlaid. Instead, the brain begins with less precise oriented estimates using simple cells. Simple cells cannot, however, respond at the ends of sufficiently thin lines. Without additional boundary processing, gaps would exist in boundaries at lines' ends. Brightness and color could flow through these gaps via surface filling in. Every scene that contains lines would thus be awash in spurious brightness and color. So spatial and orientation competition prevent this catastrophe from occurring by closing boundary gaps at line ends using end cuts. These competitive stages thus illustrate hierarchical resolution of uncertainty. They overcome the spatial uncertainty at line ends that caused by using simple cell receptive fields. End cuts do not, however, prevent all spreading of brightness and color from occurring beyond the edges of a scene. As neon color spreading illustrates, however, events like neon color spreading are rare and do not interfere with the brain's ability to effectively represent the visual world most of the time. Visual illusions like neon color spreading are also very useful probes of how the brain forms boundaries and surfaces by calling attention to properties of these processes during circumstances when they break down. The recognizing without seeing complex cells imply that all boundaries are invisible. Before output signals for simple cells reach the two competitive stages, they overcome a different kind of uncertainty. Each simple cell can respond to either a light color or a dark light oriented contrast within its receptive field, but not to both. If simple cells that are sensitive to just one contrast polarity, say light dark input to the competitive stages, then the brain would often create boundaries with big gaps in them. This would occur, for example, in responses to objects that lie in front of the textured backgrounds whose relative contrast with respect to the background reverses along the object's perimeter. Brightness and color would spread out of these boundary gaps as well, again obliterating critical scenic information. The perceptual catastrophe is averted by complex cells at which the output of like-oriented dark light and light-dark simple cells are added in each position. Complex cells can then respond to contrast of both polarities at every position along the bounding contour of an object in front of a textured background. Pulling inputs from opposite contrast polarities at complex cells implies that boundaries cannot represent visual qualia. They cannot discriminate between dark light and light-dark contrast, or red-green and green-red contrast, or blue-yellow and yellow-blue contrast, because they pull together input from cells that are sensitive to all these differences. To form the best possible boundaries, in other words, boundaries are insensitive to direction of contrast, although boundaries can vary in strength or distinctiveness as they receive input from variable numbers and strengths of inducers. They do not code for visual brightness and colors. Said in a more striking way, all boundaries are invisible. Boundaries may be consciously recognized even when they are invisible, as are the boundaries formed by reverse contrast. So boundaries are invisible, then how do we see anything? Consciously perceived quality are predicted to be surface percepts. Such surface percepts include the different surface brightnesses or colors that may occur on two sides of the boundaries after surface filling in occurs, and that thereby renders it visible and illustrates by the percept generated by a kinesis square stimulus. So these results raise the basic question, why do we consciously see? One possible answer is that we see objects to recognize them. However, the reverse contrast kinesis square percept contradicts this hypothesis by showing that invisible boundaries can be consciously recognized. In fact, there are hundreds of examples of recognition without seeing. Why then has evolution gone to the trouble of letting us see visual qualia? Our proposed answer to this question will be given in sections 10 in terms of the surface percepts that are formed. Additional information about how boundary and surface processing support invariant object category learning and recognition are needed to understand how these events are proposed to happen. This is fascinating. I'm not going to have time to read all of this, but extremely fascinating how our brain puts together vision, the picture in our head. So to summarize what has already been described, the first hierarchical resolution of uncertainty uses spatial and orientational competition to overcome boundary computing uncertainties caused by simple cells. The second hierarchical resolution of uncertainty uses bipolar grouping feedback to generate positionally sharp groupings that overcome uncertainties in initial positional fuzzy groupings. The third hierarchical resolution of uncertainty concerns why surface filling in occurs. This final hierarchical resolution will now be described. Surface system discounts the illuminant or compensates for variable illumination. An early processing stage, if this did not happen, then the brain could erroneously process changes in illumination as change in perceived object shapes and colors. If object shapes seem to plastically deform with every illumination change, then the brain could not learn to recognize a stable object percept. The discounting process inhibits luminance and color inputs as many positions across the scene surface. The process spares signals called feature contours nor positions where color or luminance changes sufficiently rapidly across space. These are typically positions where material properties of scenic objects change, not just their illumination. At these positions, feature contours can compute material properties of a surface, such as reflectances or the proportions of reflected light within each wavelength. These reflectances are insensitive to illumination changes. The computation of illuminant discounted feature contours followed by the surface filling into these feature contours within closed boundaries is the third hierarchical resolution of uncertainty. So why resonance? Three pairs of complementary computational properties of boundaries and surfaces, along with the three hierarchical resolutions of uncertainty, illustrate that there's a great deal of uncertainty in the earlier stages of visual processing in the brain. Only after the three hierarchical resolutions of uncertainty are complete and after boundaries are completed and surfaces filled in has the brain constructed a contextually informative and temporary stable enough representation of scenic objects on which to base adaptive behaviors. If this is indeed the case, then why do the earlier stages undermine behavior? The proposed answer is that brain resonance and with it conscious awareness is triggered at the processing stage that represents boundary and surface representations, and they are complete and stable enough to control visually based behaviors like attentive looking and reaching. Available experimental evidence suggests that this processing stage occurs in pre-striate visual cortical area V4. The fact that invisible boundaries can be recognized and that all conscious qualia of our surface precepts suggests, moreover, that boundaries and surface each contribute to resonances that support recognition and seeing. These resonances link visual cortex with inferotemporal cortex and posterior parietal cortex, and predictor visual resonance focus attention upon these predictive boundary and surface representations, while gaining, amplifying, and synchronizing them without destroying their representational patterns. To say more about why surface shroud resonance is proposed to be triggered at cortical area V4 and what surface shroud reference is, requires the following summary of our mechanisms. Section 7, an example of complementary computing, attention versus orientation during category learning. Object attention by a top-down modulary on center off-surround network. Complementary computing also occurs within art circuits. Indeed, the process of attentive matching by top-down expectation is computationally complementary to the process of memory search or hypothesis testing in response to mismatched inputs. Attentive matching obeys the art matching rule using top-down modulary on-center off-surround circuits that read out the learned expectations to be matched against top-down patterns. This matching process has the following properties. When a bottom-up input pattern received at a processing stage, it can anticipate its target cell if nothing else has happened. When a top-down expectation pattern is received at this stage, it can provide excitatory modularity or priming signals to cell in its on-center and driving inhibitory signals to cells in its off-surround if nothing else is happening. The on-center is modularly because the off-surround also inhibits the on-center cells, and these excitatory and inhibitory inputs are approximately balanced, 1 against 1. When a bottom-up input pattern and a top-down expectation are both active, cells that receive both bottom-up excitator inputs and top-down excitatory priming signals can fire 2 against 1, while other cells are inhibited. In this way, only cells can fire whose features are expected by the top-down expectation, and an attention focus starts to form all these cells. Top-down expectation is thus top-down conditionable and specific event that activates its target cells during a match. Conditionable means that the top-down pathways contain adaptive weights that can learn or be conditioned to encode a prototype of the recognition category that activates it. Specific means that each top-down expectation reads out its learned prototype pattern. So art hypothesis testing and learning a predictive recognition category. The art hypothesis testing and learning cycle explains why the above properties of attention matching are complementary to those orienting search. Suppose that an active recognition category reads out a top-down learned expectation that obeys the art matching rule. When a good enough match occurs between the bottom-up input pattern and the learned top-down expectation, the initially attended features can reactivate the category via the bottom-up adaptive filter, and the activated category can reactivate the attended features via its top-down expectation. The self-reinforcing excitatory feedback cycle leads to a sustained feature category resonance, which can support attention focusing and conscious recognition. Resonance can trigger fast learning of the attended or matched feature pattern, hence the name adapted resonance. One psychophysiological marker of such a resonant match is the processing negativity or PN event-related potential. For top-down expectation of a new recognition category to match the feature pattern that activates it, all its top-down adaptive weights initially have large values so they can match any feature pattern. These adaptive weights are pruned as learning proceeds, leading to learning of an attended critical feature pattern. It has been mathematically proved that such match learning can solve the stability-plasticity dilemma by creating stable categories in response to arbitrary consequences of events presented in any order. Category learning goes on within the attention system of art, which for visual categories includes brain regions such as prestriate visual cortex, intertemporal cortex, and prefrontal cortex. If learning can occur only if there is a sufficiently good match, then how is anything ever learned? Here's where complementary properties of attention matching orienting search are crucial. A sufficient bad mismatch between active top-down expectation and bottom-up input, say because the input is unfamiliar, can drive a memory search. Such a mismatch within the attention system activates the complementary orienting system, which is sensitive to the unexpected and unfamiliar events. The art-orienting system includes nonspecific thalamus in the hippocampal system. So data supporting this. So combining paradigms to expose finer details about category learning. There are now multiple neurobiological experimental markers of how category learning occurs that when combined can lead to more mechanistically targeted experiments. Among others, 1987 provided ERP markers during memory search. 2015 provides oscillatory neurophysiological markers of the interlay between prefrontal cortex and hippocampus during learning mismatch. 1992 provides neurophysiological data during hippocampal mismatch processing. 1988 provides neurophysiological data from cortical area V4 during the learning of easy versus difficult discriminations, a process that is regulated within art by a vigilance parameter. The 1988 report, Spitzer, in the difficult situation, the animals adopted a stricter internal criterion for discriminating matching from non-matching stimuli. The animals' internal representation and stimuli were better separated. Increased effort appeared to cause enhancement of the responses and sharpen selectivity for attended stimuli. All properties of art vigilance control, where higher vigilance is needed to make more difficult discriminations. Combining these various paradigms suggests experimental tests of cortical hippocampal interactions while discriminating difficulty is varied. More difficult discriminations, at least under proper circumstances, should lead to higher vigilance, more mishmash events, and thus more of the hippocampal novelty response found. Encourage people to read through the whole thing and have to skip through it because it's very long. The resonance between distributed features and compressed categories solves symbol grounding. Another kind of complementary ignorance is overcome through resonance with the attentional system and thereby solves the symbol grounding problem. When a feature pattern is activated at level F1, its individual features have no meaning. They become meaningful only as part of the spatial pattern of features to which they belong. A recognition category at level V2 can selectively respond to this feature pattern, but does not know what features they are. When levels V1 and V2 resonate due to mutual positive feedback, the attended features F1 are coherently bound together by the top down expectation that is read out by active category at F2. The attended pattern of features F1 in turn maintains activation of the recognition category F2 via the bottom-up adaptive filter. The resulting feature category resonance hereby becomes a sequence-bound state that carries information about both what category is active and what feature are represented by it, and thus embodies sufficient information to support conscious recognition of visual object or scene. Linking brain to behavior, all conscious states are resonant states, but not conversely. Our prediction is that all conscious states are resonant states, provides a linking hypothesis between brain mechanisms and psychological functions that enable our explanations of consciousness to be experimentally tested. It is the dynamic state that lights up to enable a conscious experience to occur, and not just a role of information processing. Is not, however, predicted that all resonant states are conscious states. Resonant states that are not accessible to consciousness include parietal prefrontal resonance that trigger the selective opening of basal ganglia gates to enable the readout of contextually appropriate thoughts and actions, and entorhinal hippocampal resonance that are dynamically stabilize the learning of ethnorhinal grid cells and hippocampal place cells during spatial navigation. The resonances do not include feature detectors that are activated by external senses, such as those that support vision or audition, or internal senses, such as those that support emotion because their inaccessibility to consciousness. These resonances also do not have familiar words like seeing, hearing, and feeling with which to describe them using daily language. The varieties of brain resonances and the conscious experiences that they support. Art predicts what resonance support vision, hearing, and feeling, and how resonance supporting knowing are synchronously linked to these qualia supporting resonances. For example, surface shroud resonance are predicted to support conscious percepts of visual qualia. Feature category resonance are predicted to support conscious recognition of visual objects and scenes. Both kinds of resonance may synchronize during conscious seeing and recognition. Stream shroud resonance are predicted to support conscious precepts, auditory qualia. Spectral pitch and timbre resonance are predicted to support conscious recognition of sources and auditory streams. Stream shroud and spectral pitch and timbre resonance may synchronize during conscious hearing and recognition of auditory streams. Itemless resonances also are predicted to support recognition of speech and language. They may synchronize with stream shroud and spectral pitch and timbre resonance during conscious hearing of speech and language, that build upon the selection of auditory sources by spectral pitch and timbre resonance in order to recognize the acoustic signals that are grouped together within these streams. Cognitive emotional response resonances are predicted to support conscious precepts of feeling, as well as recognition of the source of these feelings. Cognitive emotional resonance can also synchronize with resonances that support conscious quality and knowledge about them. All these resonances have distinct anatomical substrates. It cannot be overemphasized that these resonances are not just correlates of consciousness, rather they embody the subjective properties of individual conscious experience. They also enable effective behaviors to be elicited. The following sections describe what these resonances are, indicate to the degree possible in the light of available data where they exist in the brain, and itemize some of their functional roles in the control of adaptive behaviors. So, finally, section 10. Surface shroud resonance for conscious seeing of visual qualia. Surface shroud resonance are generated between V4 and the PPC. The previous description of visual boundaries and surfaces set the stage for understanding surface shroud resonances and their role in both invariant object category learning and supporting the conscious awareness of visual experiences. Several perceptual and cognitive sciences have reported that spatial attention can fit itself into the shape of an intended object. The term attentional shroud for such a form-fitting distribution of spatial attention was introduced by Tyler in 1995. An attention shroud can form when bottom-up topographical signals from an active surface representation in V4 activate PPCP cells, which then compete for spatial attention, while also sending top-down topographical exciter signals back to V4. Taking together these signals from a recurrent on-center, off-center, off-surround network that is capable of contrast enhancing, normalizing its activities. These recurrent exchange of excitatory signals combined with competitive Auditory signals help to choose a winning focus of spatial attention in PPC that configures itself to the shape of the attendant object surface in V4. The resulting surface shroud resonance between a surface representation in V4 and spatial attention in PPC corresponds to paying attention, sustained spatial attention to consciously visible surface quality. Once triggered, the surface shroud resonance can propagate top-down to earlier cortical areas such as V2 and V1, where it can attentively amplify and select consistent cell activations while inhibiting inconsistent ones, and bottom up to higher cortical areas such as prefrontal cortex. V2 and V4, recognizing occluded objects, seeing occluded surfaces and transparency. Why is surface shroud resonance assumed to be triggered between V4 and PPC? You have to skip through this. The conscious seeing, oriented, and reaching. If occluding and partially occluded objects can be recognized using boundary and surface representations that are complete in V2, then what functions are enabled by conscious 3D precepts of the unoccluded parts of the opaque surfaces that are proposed to occur in V4? The synthesis of the Facade and ArtScan models propose that the surface shroud resonance with V4 provides an extra degree of freedom, namely conscious visibility, in which to distinguish directly reachable surfaces from non-reachable ones. This need for such an extra degree of freedom seems to have arisen because of the urgent need during evolution for more powerful object recognition capacities, notably the ability to complete the boundaries of surfaces of partially occluded objects behind their occluders so that they can be recognized. Animals who could not recognize such partially occluded objects would be at a severe survival disadvantage compared to those who could. Fortunately, basic properties of bipole cells for perceptually grouping and simple feedback interactions between the boundary and surface streams go a long way to accomplish figure ground separation. If the completed parts of these partially occluded objects could also be seen, the great confusion could occur in the planning of reaching behaviors, since all occluders would look transparent, and it would seem natural to reach directly through occluding objects to the occluded objects behind them. In brief, then, there is design tension during evolution between the requirements of recognition and reaching. Conscious visibility enables the occluding parts of many surfaces to appear opaque, and thus good targets for reaching, without eliminating the ability of the visual cortex to correctly represent surfaces that are in fact transparent. Thus, the triggering of surface shroud resonance between V4 and PPC not only selects surface representations that are sufficiently complete and stable to support adaptive behaviors, but also provide a surface visibility signal to mark the opaque surfaces regions as opposed to the completed regions of occluded surfaces right behind them, to which oriented eye movements and reaching arm movements could be successfully directed. So, 1995 study proposed that the visual awareness may be related to planning of voluntary movements, but without an analysis of how 3D vision occurs. Crick also made the strong claim of what does not enter awareness, we believe, is some form of the neural activity in certain higher visual areas because they project directly to prefrontal areas that help to plan movement. This claim captures part of the current claim, but also ignores the main issue of where the brain completes 3D surface representations that separate unoccluded surface regions from one another in depth. Only after this stage can these representations be brought into consciousness by surface shroud resonance, also not specified by Crick in their subsequent analysis. It also needs to be acknowledged that reaching beyond occluders is possible and does not require conscious seeing of occluded object features. However, this skill builds upon a great deal of experience with the circular reactions that support direct reaching behaviors during development. The link between object learning, recognition, and seeing. Concept of surface shroud resonance was discovered during the development of the family of ArtScan models, 2009, whose culmination is currently the 3D ArtScan search model, 2014. The 3D ArtScan search model proposes explanations of data about visual consciousness that go beyond the role of surface shroud resonance in regulating learning about the invariant recognition categories that enable us to know about the objects that are consciously seen during the corresponding surface shroud resonance. In particular, this model helps to explain how consciously visible surface precepts are computed in retinotopic coordinates, even though the perceptual stability that is experienced during eye movements is achieved by computing attentional shrouds and head-centered coordinates that are invariant under eye movements. Nice chart. I'm going to have to skip through quite a bit of this. Encourage people to read it. I've already read through this more than twice. Explaining data about visual neglect, coordinates, competition, grouping, and action. After a delay of 20 years, Grossberg finally had enough evidence to propose that surface shroud resonance played this role. The hypothesis that a surface shroud resonance has is generated between V4 and PPC helps to explain various data about visual consciousness, such as data about visual neglect. These complexities, the main fact about visual neglect is immediately clear from the most basic properties of a surface shroud resonance. The very fact that visual neglect occurs at all when an appropriate region of parietal cortex, such as IPL, is lesioned, is immediately clarified by the proposed role of a surface shroud resonance in visual consciousness. Assuming the IPL is part of the PPC anatomy that supports surface shroud resonance's lesion of IPL will prevent the corresponding visual surface representations in V4 from reaching consciousness. Despite the apparent simplicity of this assertion, this hypothesis can also explain subtle clinical properties of visual neglect. Classical article 1998 reviews visual neglect properties in individuals who have experienced IPL lesions, particularly the right hemisphere. Text below takes as explanatory targets properties emphasizes in that article, which includes the following. Fascinating. Have to skip through a lot of this, but because there's too much to read through. Okay, sorry. There's a lot here. I'm sorry for the dead time. I encourage people to read this. Very complicated, a lot of stuff here. Perceptual stability, binocular fusion during eye movements. Predictive remapping of gain fields is not only used to maintain shroud stability, it also directly impacts how 3D scene is consciously seen as it is scanned with eye movements. In particular, it seems obvious that a brain seamlessly maintains binocular fusion as eye movement occurs, thereby supporting stable percepts through time of the world in depth. This apparent simplicity disguises complex underlying machinery, as can be realized by noting that each eye movement causes each of our foveas to process a different set of scenic features on each retina. There could be temporal breaks in binocular fusion after each eye movement if fused boundaries were computed only in retina and optic coordinates. Such breaks are not, however, consciously perceived. Although perceptual stability during eye movements is so familiar it does not initially seem to require explanation, this is no longer the case when we binocularly fuse a random dot stereogram or a magic eye audio stereogram in which the number of salient fusible features is less than the typically natural scene. It may take tens or hundreds of milliseconds to initially binocularly fuse the left and right eye images in these stereograms. Two types of perceptual stability cooperate during active conscious vision. We can now reconcile the claim that a surface shroud resonance has its generator in V4 and PPC, even though various critical perceptual processes occur in V2 and V1. A surface shroud resonance is triggered when the filled in 3D surface representations of V4 are complete and stable enough to support the resonance excitatory feedback and interactions. These resonant signals can then also propagate down to V2 and V1, where they can select and focus attention upon signals at these levels that support the ongoing resonances. The main new fact is that binocular boundary signals in V2 also contribute to perceptual stability. They're transformed from retrotropic into head-centered coordinates using gain fields in order to retain the stability of their binocularly fused boundaries during eye movements, and then are converted back from head-centered to retrotropic coordinates, again using gain fields in order to maintain the stability of consciousness, seen binocular surface representations that are computed in retrotropic coordinates. In summary, the simulated interactions that are summarized include the minimal number of processing stages and gain field mediated coordinate transformations that are needed to maintain perceptual stability of consciously seen surface quality as eye scan a scene. Seeing and knowing, synchronous surface shroud and feature category resonance. Often we consciously see a familiar object, we also know what it is. Our proposal that these two kinds of awareness are due to different kinds of resonances, with knowing what is seen supported by feature category resonance that include what stream regions such as IT, and conscious seeing supported by surface shroud resonance that include warehouse streams regions of PPC. How then do we know what a familiar object is when we see it? Our proposes that this happens because both resonance interact with shared visual cortex areas such as V4 and can thus synchronize with each other, often with gamma oscillations. What and where house streams for audition. The concept of surface shroud resonance was published before the current article was written. However, the way in which the current article unifies the discussion of the visual processes that feed into it and why, and its implication for consciousness and the control eye movement and reaching are new. Also new are explanations of various visual databases that this synthesis enables. The summary of how multiple brain regions interact to learn, recognize, and search for valued visual objects also implies multiple testable neurobiological predictions about these processes work. Various of the discussion herein of the auditory and speech perception, the production processes also represent new syntheses of separating separate model streams. Other explanations are new, such as predicting homologue between visual circular reactions per motor equivalent reaching and auditory circular reactions per motor equivalent speaking, and the concept of stream shroud resonance that support conscious hearing. So too are concepts that built upon these insights about how auditory consciousness may work, and explanations of various data about topics ranging from auditory neglect to rhythmic performance of speech and songs. So ventral sound to meaning and dorsal sound to action, complementary invariance, the concept and processes that have helped understand aspects of conscious visual perception would now be useful towards explaining properties of auditory consciousness because there are strong homologues between the cortical systems that process vision and audition. Indeed, what and where how streams for auditory processing have also been described with a ventral pathway into the anterior temporal cortex that carries out identification of complex auditory patterns or objects, and a dorsal pathway into posterior parietal cortex that carries out spatial processing. 2007 study summarized the dichotomy by linking the ventral pathway with sound to meaning and the dorsal pathway with sound to action. In other words, auditory as well as visual processes are organized into computationally complementary cortical processing streams. How complete is the homologue that is suggested by the fact that both auditory and visual processing use temporal and parietal cortices? If the homology is strong, what type of auditory properties should we expect from it? In attempting to answer this question, one needs to acknowledge that both auditory and visual processing compute invariance to be effective. For example, conscious seeing uses radionoptic surface representations and head-centered shrouds to maintain perceptual stability during eye movements, thereby both stabilizing conscious precepts of visual qualia as the eye moves, enabling visual recognition of categories to be learned that are significantly invariant under changes in object view, position, and size. What mechanisms maintain perceptual stability of auditory conscious precept, and what kind of invariants are learned by auditory recognition categories? In the auditory domain, any mechanistic satisfying answer to this question would address at least part issues as how can a young child babble sounds in one set of acoustic frequencies and use them to learn how to imitate sounds from teachers who speak using different frequencies? How can codes from speech and language meanings be coded into speaker invariant and rate invariant way in order to prevent combinatorial explosion of stored memories? Much as learned visual object recognition codes are invariant under view, position, and size, despite the fact that these speakers and rate invariants are now present in acoustic signals. How can speakers' identity be learned as well, so that different voices can be consciously heard and recognized? How do these distinct speaker invariant and speaker sensitive representations interact to understand the meaning and identity of the identifiable acoustic source? How can rate invariant codes for speech be performed and experienced at variable rates that are under volitional control? How can invariant codes be performed as the lyrics of songs with different rhymes and pitches? The section below proposes answers to these questions that illustrate contemporary complementary processes of art resonance operating at multiple levels of the auditory system, just as they do in the visual system, to support conscious auditory experiences while stabilizing learning of auditory representations along the way. The text outlines an emerging unified neural system that combines modeling discoveries which have been developed to explain distinct databases about audition, speech, and language in order to achieve the synthesis. A new idea about the mechanistic neural substrate of conscious auditory experience are proposed, and explanations of many additional data are provided for the first time to support these ideas. A great deal of additional experimental and theoretical work can properly be done to further develop this theoretical foundation. Circular reactions in vision and audition, babbling to reach and speech. A helpful way to understand auditory visual homologs is to consider the perception action circular reactions that occur during auditory and visual development. During visual circular reaction, babies endogenously babble hand-arm movements and reactively foveate their moving hands, thereby learning a map from hand positions to eye positions and from eye positions to hand positions. After map learning occurs, looking at a target position can trigger a command that is under volitional control for the hand arm to reach the target. During auditory circular reaction, babies endogenously babble sounds and learn a map between auditory feedback from these sounds and the commands that produce them. After a sufficient amount of map learning occurs, a child can use it to imitate sounds from adult speakers and thereby begin to learn and perform speech and language, again under volitional control. Motor equivalent reaching and speech production, tool use and co-articulation. We have to skip through a lot of this. I wish I could read this all aloud. Stream shroud resonance for conscious hearing of visual qualia. Auditory scene analysis, tracking sound sources through noise and overlapping frequencies. Auditory continual illusion and spectral pitch resonance. Itemless resonance for recognition of speech and language. From streaming to speech, item and order working memories and list chunks, art mechanisms also operate at higher cortical levels of the auditory system, whereby they help to clarify how speech and language are rapidly learned, stably remembered, flexibly performed, and consciously heard. These art models have been developed as part of an emerging neural theory of speech learning, perception, recognition, recall, whose various increasing developed models are called phonet, art phone, art word, and conscious art word, and C art word. This theory proposes how sequences of acoustic item chunks are stored temporarily in working memory before being categorized by list chunks. The term working memory here is used to mean the temporal storage of sequences of events through time, not just persistent storage of a single event. The subsequent text summarizes enough information about these models to clarify how they interact with the stream shroud circuits that determine conscious hearing and the spectral pitch and timbre resonance that determine the stream upon which these higher cortical order processes build. So Grossberg, 78, introduced a neural model of working memory upon which the more recent models listed above consistently built. This item and order working memory model posits the temporal stream of inputs is stored through time as an evolving spatial pattern activity across a network of content addressable item representations. Input to the working memory are unitized item chunks of individual sounds An item chunk is a learned recognition category that selectively responds to a spatial pattern of activation across a network of auditory features and detectors during a brief time interval. Active item chunks input to the next processing stage, where sequences of them are stored in real time with a working memory. The temporal to spatial transformation converts the input sequence into a temporally evolving spatial pattern of activity or activity gradient across item selective cells. The relative activities of different cell populations code the temporal order in which the items will be recalled, with the largest activities recalled earliest, hence the name item order working memory for this class of models. A primary gradient in which the first item stored is the largest activity, the second, the next largest activity, and so on, can be recalled in the correct order. Recall occurs when a nonspecific rehearsal wave opens all the output gates of a network, thereby enabling the most active item chunk to be read out first. As it is read out, it self-inhibits its stored activity, thereby enabling the next chunk to be read out, and so on until the entire stored list is performed. A more recent name for this class of models is competitive queuing. When an item in order working memory can store repeated items in the sequence, it is called item order rank working memory. Item order rank working memories, including the role of primacy gradients, incorrect list storage, and recall, are supported by psychophysical and neurophysical data. These stored working memory sequences are unitized through learning into list chunks or sequence category representations at the next processing level. List chunks can be selectively activated by different item sequences during speech perception and word recognition. So top-down attentive matching and item list resonances, top-down expectation signals from the list chunks are activated as the items being stored in working memory through time. These top-down expectations satisfy the ART matching rule and thereby select consistent item sequences while inhibiting inconsistent ones to create temporarily evolving attention focus. As the cycle between bottom-up activation and list chunks and top-down attentive matching of an item sequence continues through time, an item list resonance can develop whose list chunks represent the best prediction of what item chunk sequences are attended at any given time within working memory. Such an item list resonance is proposed to support conscious recognition of attended speech and language representations when it interacts with lower level resonance such as stream shroud and spectral pitch and timbre resonances. So phonemic restoration, how the future can influence what is consciously heard in the past. Phonemic restoration illustrates the operation of ART mechanisms during speech perception in much the same way as the auditory continuity illusions represent them during auditory streaming. Suppose the broadband noise replaces the phoneme B and B in the words delivery and deliberation respectively, despite the identical initial position of these words. If the broadband noise is immediately followed by airy or oration, listeners hear the V and B as being fully intact. However, the noise is replaced by silence. The restoration does not occur. These experimental properties of phonemic restoration match properties of top-down matching by the ART matching rule. Thus, phonemic restoration properties illustrate attentive matching processes that enable speech and language to be learned quickly without risking catastrophic forgetting. In the case of speech perception, the categories that are learned represent phonemes, syllables, and words rather than the pitch and timbre categories that are learned during auditory streaming. Phonemic restoration also illustrates temporal properties of consciously heard and recognized resonance that emerge through time as items are temporarily stored in working memory. In particular, the noise in belly noise is not consciously heard and recognized before the last portion of the word occurs, because if the resonance is not developed fully before the last portion of the word is present, then the portion can influence the expectations that determine the conscious precept and meaning. As this resonance unfolds, its expectations convert noise into a precept while suppressing spectral components of the noise that are not part of the expected consonant sound. Variation of this experiment in which a reduced set of spectral components is used in the noise leads to hearing a corresponding graded consonant sound. As the case of the auditory continuity illusion, future events can influence past events without smearing over all the events that intervene. Again, this is due to the fact that top-down attentive matching process is modulatory. The opposite concern is also of importance. How can sharp word boundaries be perceived, even if sound spectrums that represent the words exhibit no silent intervals between them? ART proposes that conscious speech is a resonant wave, in that silence is a discontinuity in a rate at which resonant waves evolve. The top-down matching process coherently groups familiar linguistic units together through time, even if they are not separated by silent intervals in the input system. The auditory continuity illusion and phonemic restoration support the hypothesis that multiple levels of auditory processing use resonant dynamics to coordinate fast learning, self-stabilizing memory, and conscious awareness of different types of auditory information. So shared design for linguistic, motor, spatial working memories, long-term memory invariance, and normalization. So what properties recommend item and order working memories more than other possible alternatives over and beyond their broad explanatory and predictive range? Normalization rule insists that working memory's maximum total activity tends to be independent of the number of stored items. Thus, if more items are stored, then each item tends to be stored with less activity. Normalization implies a limited capacity of working memory by redistribution rather than simply adding activity when new items are stored. Both postulates are automatically satisfied by ubiquitously occurring neural design, thereby clarifying how working memory could arise through evolution. This design is recurrent on-center, off-center network whose cells obey shunting dynamics. Because of the shared design, it becomes easier to understand a language, and young children can begin to develop in a way that parallels the motor behaviors of adult teachers during mutual play, or else sign language by hearing adults can coordinate signing with speaking. In summary, figure ground separation and vision may be compared with streaming and audition in speech perception. If these visual and auditory processes have homologous brain designs, then the auditory analog of V4 and visual surface representation may be sought by future research in the anatomical substrate of auditory streaming. A spectral pitch resonance has some of the required properties to support conscious precepts of auditory streams, but the resonance that support conscious hearing cannot be restricted only to the sustained sounds that support pitch precepts. As explained in section 17, both transient and sustained feature detectors are needed to consciously hear, understand, and perform the sounds of the rule. Section 17. Learning and storage of speaker invariant and rate invariant working memories. Multiple working memories and list chunking networks in the what and where how auditory cortices are used to encode sounds. Some of these working memories and list chunking networks embody frequency and rate sensitive processes like voice, instrument, and speaker identification, whereas others embody frequency and rate invariant processes such as speech and language recognition and meaning. Speech speaker normalizations in the what stream, circular reactions, and imitative maps. Speech signals are speaker dependent, but what stream representations of language meaning are speaker independent. The transformations from speaker dependent to speaker independent language representations enable speech to be learned and understood from different speakers. This process is called speaker normalization. Speaker normalization allows language learning to get started. Circular reaction enables a baby to learn a map between the auditory feedback from its own babbled sounds to the motor commands that cause them. For the baby to imitate sounds of an adult teacher who speak in a different frequency range, both the baby's sounds and those of the adult teacher need to be filtered by a network that normalizes them into a common frequency range. After speaker normalization is achieved, an imitative map can be learned from the baby's speaker normalized babble sounds to the motor commands that produce them. Subsequently, the speaker normalizes processing stage enables the imitative map to filter heard adult sounds into novel speech production using the learned connections from the normalized babbling sounds to the motor commands. These imitated sounds can then be refined by speech and language learning experience throughout life. Learning in the imitative map remains active for many years to enable individuals changing voice through puberty and adulthood to update the map. This fact raises two design problems. What process dynamically stabilizes the map learning process while also allowing the map to undergo controlled changes? What process ensures dimensional consistency for the auditory speech representation and motor speech commands that are linked by the map so that the map can in fact be learned? So the art architecture incorporates a solution to both problems. In it, babbled sounds are generated by a VITE circuit. When it is activated by an endogenous random generator during speech circular reaction, these babbled sounds create auditory feedback, thus activate acoustic feature detectors. At the same time, that this circuit was published in 1988, it was not yet understood how speaker normalization might occur, so that acoustic features were simply said to be invariant, that is, speaker normalized at the model's invariant features detector level. These speaker normalized feature patterns are partially compressed into multiple auditory item chunks, which are then associated through learning via the imitative map with the still active motor synergy commands that produce the babbled sounds. This learned auditory to motor imitative map is rendered dimensionally consistent and temporarily stable to motor and auditory learned expectations that use the art matching rule to attentively select and learn auditory feature patterns that are consistent with the active motor commands. The motor to auditory selection process mechanistically explicates the motor theory of speech perception. Subsequent processing stages for learning item chunks, storing sequences, item chunking, and working memory, and learning lists of chunks of these stored sequences use the mechanisms that were outlined earlier in section 16 and further explicated below. These sequence processing stages occur after the speaker normalization stage and thus enable language meanings that were learned from one teacher's voice to be understood when uttered by another speaker. So from auditory streaming to speaker normalization, stared circuit design. So how does speaker normalization occur in the brain? How can evolution be smart enough to discover speaker normalization? Section 16.4 proposed that working memories are just specialized recurrent shunting on-center off-surround networks, which are ubiquitously because they solve the noise saturation dilemma. Has the brain specialized another broadly used design to accomplish speaker normalization? The neural normalization network model proposes that speaker normalization specializes the same kind of neural mechanisms that are used to form auditory streams. The proposal offers a parsimonious solution to speaker normalization problem because it is only after acoustic sources, including speakers, have been separated from one another by streaming that they can be speaker normalized, just as it is only after visual figure ground separation occurs that invariant visual categories can be learned. Speaker normalization specializes streaming mechanisms at the next processing stage. From speaker normalization to rate normalization, learn codes for speech and language and meaning need also to be rate invariant to understand multiple speakers talking at variable rates. Many features of speech signals are, however, not preserved at speech rate changes, so rate invariant representations must be actively constructed by the brain. Human listeners can also consciously hear and understand particular voices speaking at variable rates, and human speakers can use their speaker and rate invariant representations of meaning to speakers sing in their own voices and at their own volitionary controlled rates. How the brain accomplishes these various competences and how they are consciously heard and recognized will be proposed below. 3 additional design features are needed to solve the rate invariant problem. Sustained and transient streams. Parallel cortical streams exist for processing sustained versus transient acoustic features to represent all the sounds that occur during audition, speech, and music. Intra-word rate invariants gain control signals from the T stream to the S stream, compensate for non-invariant changes within syllables, such as consonant-vowel pairs. As speaking rate changes, this interaction creates more invariant ST ratios across rates. And inter-word rate invariance, rate-dependent gain control adjust the integration rates of working memory and list chunking networks as the overall speech rate changes across syllables. This process generates more rate-invariant storage of speech and language representations in working memory and list chunking networks. Each process will be reviewed briefly. Transient and sustained processing streams on audition speech. The brain's auditory system includes sustained cells that are sensitive to particular frequencies over time, the transient cells that are sensitive to FM sweeps across multiple frequencies at a particular rate of detection. It was modeled 1997, how co-articulated consonants and vowels may activate distinct but parallel transient T and sustained S channels, and how these selectively helps to explain data about auditory nerve processing. The S channel can be discriminate synchronous vocalic quality while suppressing transient speech signals. The parallel T channel can discriminate onsets and offsets of fricatives and stop consonants, as well as detect vowel onsets and offsets. So phonet. Asymmetric T to S gain control creates within syllable rate invariance. A faster speech rate may be more strongly activate transients in speech signal but leaves less time to integrate sustained signals. Thus, faster rates can change the relative activities of T and S cells, which T cells being favored. Such rate-dependent changes in relative T and S activities could cause serious problems for learning speech codes because the bottom-up adaptive filter pathways tend to activate the same set of chunks when their relative activities across the network are preserved. A more rate-invariant TS ratio is created by letting TNS inputs activate their own working memories, after which excitatory signals from the T working memory increase the integration rate of the S working memory, thereby compensating for the relative strengthening of T relative to S activation as speaking rate increases. Several experiments have reported such asymmetric vocalic context effects from T to S, but not conversely, and psychophysical experiments support the importance of consonant-vowel ratio as a cue for voicing in English. Rate-sensitive gain control creates rate-invariant working memories. Taking together these two sorts of gain control, one acting within individual words and the other acting across sequences of words, begins to explain how a rate-invariant speech representation may be created internally by brain dynamics from variable rate speech signals that do not themselves exhibit properties of invariance. How rate-dependent productions and their conscious precepts via auditory feedback can be created from these rate-invariant representations we described in section 18. This kind of gain control helps to explain paradoxical properties of psychophysical data about conscious speech perception and recognition. In brief, the heuristic ideas are as follows. Listener precepts are approximately invariant with respect to mean silent interval between stop consonant clusters. Durations of silent intervals are inversely related to the speech rate. The speech rate alters the working memory integration in list chunking networks. Integration rates via T-sensitive gain control. The result is a tendency to retrieve a rate-invariant precept. Paradoxically, this rate-invariant precept can produce rate-dependent category boundaries of heard speech. Classical phenomenon studied by Rep in 1980. Oh, section 18. From invariant working memory storage to volitionally variant productions and precepts. This section summarizes how speakers in rate-invariant working memories and list chunking networks can recall their learned representations of voice-specific and rate-variant productions that are matched against auditory top-down expectations and consciously heard. When a stream shroud resonance develops in response to a good enough match, the networks are successfully generalized to enable variable rate productions without and with the learned rhythm, and without and with the singing voice. Further development of these modeling concepts and mechanisms is needed to process realistic speech and music. The volitionally controlled variable rate sequential performance. First example proposes how recall from working memory can occur in an individual's usual speaking voice with the production of rate control by a volitional go signal from the basal ganglia. So in order for such coordination to work, the readout of the next working memory command must be timed to take into account when the current production is almost executed, even if the performance can occur at variable rates. How does the knowledge about the state of current production influence the timing of working memory readout, given that these two processes occur in separate networks and compute different kinds of information? I have to skip through more of this, trying to finish up here. Learning of invariant list rhythmically intonated performance. List parse and its various extensions clarify how changing the amplitude of a volitional signal can, on a moment-to-moment basis, vary the speed at which stored sequences are performed, albeit useful. This simple form of rhythmic performance is insufficient to explain the more sophisticated rhythms that occur during natural speech and singing. These competencies depend on a brain design that supports a flexible relationship between stored order information and the pitch and rhythm, which with the it is performed, in particular when a listener hears a sufficiently short segment of novel speech that is uttered with one rhythm, he or she can immediately perform it with the same rhythm or with a different rhythm that the listener chooses. Thus, the rate invariant order information of the sequence can flexibly be decoupled from and later recoupled with one of several possible rhythmic productions. I like to call this property factorization of order and rhythm for the following reason. The speech item and their order can be stored in the rate invariant item order rank working memory. The fact that a sufficiently short stored order sequence after one hearing can be performed with the same rhythm or with a different rhythm shows that separate systems with working memory properties exist for storing the rhythm. The fact that the stored rhythm does not have to be used for the performance shows that the parallel order and rhythm working memories can operate independently from each other under volitional control. This property is related to the so-called independence of lyrics and tunes that occurs when hearing or performing vocal music. A big caveat to such independence is that these two types of information interact during storage when the heard order information influences the perceived timing and storage of the tune's pitch, contours, and rhythm, and again during production when order, pitch, and rhythms information are combined to yield the final performance. These interactions are the reasons why the term factorization is preferred to independence of order, pitch, and rhythm herein. Indeed, the learned list chunks that are stored in rate invariant item order rank working memory help to determine what rhythm is perceived and separately stored, much as how the learned chunks of a language may influence its perceived rhythm. From speaking to singing. One more interaction between complementary process streams will now be briefly noted. Order and rhythm information is stored within working memory, whose inputs are speaker normalized. These working memories read out their commands to representations that control the speaking voice of the performer. The inner stream interaction builds upon the learned circuit reaction that was discussed in section 14 between speaking and hearing that occurs throughout life. Learning also goes through life a parallel circular reaction that links learned spectral pitch and timbre categories for the recognition of heard sounds, which are not speaker normalized, to the motor synergies that control the pitches generated by the vocal folds. Sequences of these pitch-sensitive categories can be stored in spectral working memory as a melody or song. When a speaker and rate invariant working memory or rhythm working memory and spectral working memory are concurrently read out, coordinated by the basal ganglia, then learned language sequences at a given rhythm can be produced with the series of pitches characteristic of a song. The main point for conscious audition is that these working memories read out production commands at the same time as they read out top-down sensory expectations of the sounds that are expected to be heard. When these expectations are matched by the auditory feedback of the productions, the song is consciously heard by coordinated stream, shroud, and spectral pitch and timbre resonances. These resonances also support conscious precepts that heard sounds that are emitted by the external world. More modeling needs to be done to carry out large-scale simulations such as coordinated resonance during the control of real-world auditory behaviors. The feeling of what happens, cognitive emotional resonance for conscious feelings, resonance between object value and object value categories beyond Chomsky and Skinner. The visual and auditory processes summarized above represent external information about the world, but they do not evaluate how important this information is for survival and success. Interaction between perceptual, cognitive, and evaluative reinforcement emotional motivational mechanisms accomplish this. What kind of resonance supports a conscious emotion? What kind of resonance enables an emotion to generate a conscious feeling of what happens? Knowing the source of that feeling and being able to behave in an appropriate way in response to it. In particular, how does an emotion generate motivation that may help to search for or acquire goal objects that can satisfy that emotion? Under what circumstances can emotion affect behavior without being conscious? How do breakdowns in these resonances lead to prescribed mental disorders such as autism and schizophrenia? And how does the effective meaning of familiar objects and events fail to organize behavior in context-appropriate way when this happens? The study of cognitive emotional interactions and the conscious resonance that they support is needed to propose answers to these questions. Such resonance focus motivated attention upon valued objects in an adaptive, timed way. Unlike visual and auditory conscious precepts, emotions or feelings do not represent external sensory cues such as sights and sounds. Rather, they represent internal affective states of fear, pleasure, pain, happiness, sadness, and the like that may be activated by a variety of external and internal signals. When conscious emotions are triggered by viewing effective, meaningful visual senses, cognitive emotional resonance are proposed to support these feelings. Our knowledge of them and our ability to respond appropriately. These resonances occur using feedback interaction between invariant object categories for recognition of objects, also called object categories and temporal cortex. Value categories or drive representations in the amygdala, where reinforcing and homostatic inputs converge, from which motivational signals emerge. Homostatic representations in the hypothalamus that register and control automatic and offer effective restrictions, and object value categories and orbitofrontal cortex, to which object categories and value categories both send their output signals. The object category representations may in turn synchronously interact with service shroud and stream shroud resonance that support conscious awareness of the visual auditory events that activate object categories. Neural modes of cognitive emotional resonance began in the articles Grossberg in the early 70s, at a time when there was a major split between studies of cognition, as exemplified by the work of Chomsky in 57 in linguistics and emotion, and exemplified by the Skinner 1938 on instrumental conditioning. Skinner's anti-theoretical behaviorist stance opposed any model development. Chomsky's universal grammar formalized included no dynamic, let alone learning dynamics, and was devoid of any allusion to emotion. Instead, cognition and emotion studies were often antagonistic to each other, as illustrated by the critique of Skinner's behavioralism and Chomsky. Such divided concepts of cognition and emotion have persisted during many historical periods, as described in the book Wittgenstein's Vienna in 1996. The Grossberg article began a mechanistic synthesis of cognition and emotion by showing how the same kinds of neural equations and modules suitably specialized could interact during a cognitive emotional resonance to join what we know with what we feel. As summarized below, the resurgence of effective neuroscience in the intervening years has supported all the predictions that grew out of this emerging synthesis. Reinforcement learning, conditioned reinforcer, and incentive motivational learning. Many visual cues do not initially have effective meaning to an individual. These cues can acquire effective significance through reinforcement learning, whereby the pathways between the object value, and homostatic representations can be altered. For simplicity, consider only the simplest kind of reinforcement learning, called Pavlovian or classical conditioning, during which a conditioned stimulus that initially may have no emotional significance is paired with an unconditioned stimulus that can, from the start, generate a strong emotional response. Before conditioning occurs, when a familiar conditional stimulus occurs, the conditional stimulus can selectively activate an object category. The object category can, in turn, send priming signals to most or all of the value categories, but cannot vigorously fire any of them. It can also send primary signals to the object value category. Neither the object value category nor the value categories can fire vigorously in response to a conditioned stimulus before reinforcement learning occurs. So when a conditional stimulus is suitably paired in time with a universal stimulus, reinforcement learning can begin. The universal stimulus can activate the amygdala value category and hypothalamic homostatic representations that correspond to the emotion it engenders. As a result, the conditioned stimulus activated object category and universal stimulus activated value category are simultaneously activated, so that learning can occur in the pathways from the active object category to the active value category, thereby strengthening the learned connection between them. After sufficiently many learning trials, the conditioned stimulus can activate that value category. When this happened, the conditioned stimulus is said to have become a conditioned reinforcer. As a conditioned reinforcer is being learned, the value category that is activated by the universal stimulus is able to send signals called incentive motivation signals to many object value categories, including the object value category of the conditioned stimulus. When this occurs, convergent signals from both the object category and the value category converge on the object value category. Such convergent signals are sufficient to activate the object value category. Now both the value category and the object value category are simultaneously active, so learning can occur in the pathway from the value category to the object value category, further strengthening it while weakening pathway connections to inactive object value categories. This strengthening is called incentive motivational learning. After both conditional reinforcer learning and incentive motivational learning occurred, the conditioned stimulus activated object category can prime its object value category and activate its value category. Then convergent input to the primed object value category from both the object category and the activated value category can fully activate the object value category, and with it motivated behaviors, after a value category is conditioned to sufficiently many CS activating just a value category can generate an emotional set by priming all of the object value categories with which it was associated in the past. After an object value category gets activated, it can generate top-down priming signals to its object category via the art matching rule. The importance of this feedback pathway can be seen by considering situations where multiple visual cues occur simultaneously. If after competition occurs between the object value categories, the most active object value category reads out its top-down attention signal to a currently active object category, it can amplify and thereby help to select this motivationally consistent object category, while the competitive interactions in the off-surround of the art matching rule intentionally block object categories of motivationally irrelevant sensory cues. Activation of the feedback circuit through temporal, amygdala, orbital frontal interactions can create a cognitive emotional resonance that focuses and maintains motivation attention upon a motivationally salient object category, while also supporting conscious feelings about the object, enabling the release of motivationally compatible actions. This kind of cognitive emotional resonance was first predicted by the cognitive emotional motor model and was used to quantitatively explain and simulate these in later articles parametric properties of many cognitive emotional data. Predictions of the cognitive emotional motor model have been supported by subsequent data, notably data concerning the anatomy and neurophysiology of the brain regions that the model interactions functionally explain. So confidence in the cognitive emotional motor model predictions about the role of cognitive emotional resonances in conscious feeling, knowing, and acting grows with the amount of interdisciplinary data that this model and its extensions can explain and predict. To this end, further developments in the cognitive model, such as matching objects to internal value triggers, options, revaluations, or motivar model, proposed how amygdala, hypothalamus, and basal ganglia carry out complementary roles during reinforcement learning, and simulated neurophysical data about infratemporal, amygdalic, orbitofrontal, and hypothalamic cell dynamics during the learning process, including the discharge dynamics of known cell types that predict saccadic reaction times and the CS-dependent changes in systolic blood pressures, while stimulating data about food-specific satiety, Pavlovian condition, reinforcer devaluation, and simultaneous visual discrimination. In particular, in response to a conditioned stimulus, the model amygdala and hypothalamus interact to calculate the expected current value of the subjective outcome that the conditioned stimulus predicts, constrained by the current state of deprivation or satiation. Model amygdala cells are called value categories because they respond selectively to different patterns of activation across hypothalatic homostatic cells, thereby categorizing the homostatic substrates of different emotions. These value categories also send top-down signals that obey the art matching rule back to their hypothalamus sources and thereby dynamically stabilize the learned amygdala value categories and intentionally bias homostatic responses. The amygdala category also project their expected value information to orbitofrontal object value category cells that also receive inputs for temporal object category cells, activating orbitofrontal cells by conjoint inputs from object and value category codes, the subjective values of objects. These values guide behavioral choices via the output signal from orbitofrontal object value categories. So interactions, skip through. So the feeling of what happens, core consciousness, dual competition, and survival circuits. 1999 study derived from clinical data what can be viewed as a heuristic version of the cognitive model and has been used to describe what can be interpreted as a cognitive emotional resonance that support the feeling of what happens. Translating this concept map of object X becomes an invariant object category. The map of the proto-self becomes the value category, and its multiple interactions in the second order map become the object value category, and the map of object X is enhanced becomes the object category as it is attentively amplified by feedback from the object value category. As this cognitive emotional resonance develops through the excitatory feedback loop between object value and object value categories, the attended object achieves emotional and motivational significance. This cognitive emotional resonance binds together with complementary aspects of object categories and value categories in much the same way that feature category resonance binds together complementary properties of distributed features, and that object categories in the Kagan model, the invariant object categories, can classify particular combinations of features in the world but cannot compute their value to an organism. Activation of a value category sets the stage for thoughts and actions that have a particular emotional, motivational meaning, but does not represent any particular object or events to which these feelings could be directed. The bound state of the cognitive emotional resonance combines facts about the external world with feelings about motivations to act from the internal world. Attention is driven to focus on an object, and the result of saliency of the images of that object in the mind, leading to what Damasio calls core consciousness. Damasio also went to write, I do not know how the fusing, blending, and smoothing are achieved. The Kagan model began to provide explicit explanations of how this happens in the brain, starting 28 years before Damasio wrote these words. As a case of surface shroud resonance, a Kagan cognitive emotional resonance is predicted to propagate the other brain regions with which its object value and object value categories interact, including hypothalamus, visual cortex, and other prefrontal cortical areas, including areas that control executive planning and action. A region like the hypothalamus is particularly important because it controls internal homeostatic states whose activation patterns correspond to different emotions. As a result of such a cognitive emotional resonance, the feeling of what happens can ascribe feelings to particular objects and events in the world, activate sensory expectations of what one would like to happen next, and activate behaviors to achieve valued goals. The Kagan model is also consistent with more recent proposals. These include the dual competition model, 2009. The proposed framework is referred to as the dual competition model to reflect the suggestion that affective significance influences competition at both the perceptual and executive levels. And because the impact is caused by both emotion and motivation, these two competitive stages correspond to the object and object value stages in Kagan. The survival circuit concept integrates ideas about emotion, motivation, reinforcement, and arousal in the effort to understand how organisms survive and thrive by detecting and responding to challenges and opportunities in daily life. The Kagan and motivator models propose how these processes are integrated to generate appropriate learned behaviors in response to unique environmental challenges, especially when they're combined with perceptual, cognitive, and motor circuits in larger systems. Such larger systems have been embodied in adaptive mobile routes. So breakdowns during mental disorders, theories of mind, autism, and schizophrenia. So when Kagan circuits functions improperly, symptoms of mental disorder can result. For example, hyperactivity of amygdala or overfrontal cortex can prevent a cognitive emotional resonance from occurring, thereby causing failures of the theory of mind processes in both autism and schizophrenia. Such failures incur problems with activating motivationally directed goals and attention. This happens in Kagan when a depressed emotional response in the amygdala also depresses the incentive motivational signals needed to activate prefrontal cortex in response to motivational salient events. The prefrontal cortex will then not adequately activate, and a hypofrontal condition can emerge during which working memory and representations and plans are degraded, so social goals and plans will not form normally. Depressed emotional responses to environment and internally generated cues include facial expressions combined with insufficient motivational support for emotionally appropriate plans and actions, helps to explain why individuals with autism may be unable to understand others' actions and may themselves perform actions that are socially inappropriate. Deficiencies in theory of mind are not, however, sufficient to explain all aspects of autistic development and behavior. ArtScan skirts solving the Where's-Waldo problem. Survival circuits can solve the Where's-Waldo problem by being able to search for and recognize important goal objects in multi-object scenes, including readout of sensory expectations, whose matching by acquired target can elicit a conscious precept of the target before launching appropriate goal-oriented actions towards them. The ArtScan search model scan proposes how this may happen. So ArtScan search shows how object categories that are learned with view size and positionally invariant properties in the what cortical stream can activate positionally sensitive or dependent representations in the where cortical stream that can be used to act upon a value object space. To accomplish this feat, ArtScan search builds upon the ArtScan and Kagan models. In particular, ArtScan model that was summarized in section 12 used where to what interactions to modulate the learning of invariant recognition categories. The ArtScan search model supplements these where to what interactions with what to where interactions that can guide directed search and action towards value goal objects whose representations are selectively amplified by motivated attention. ArtScran search uses cogm to find a desired target object in a scene through bottom-up simulation by the scene, and a top-down motivational search. ArtScran search also simulates how executive prefrontal cognition primes can drive such a search. ArtScran search can find a Waldo by exploiting how ArtScran learns invariant recognition categories. Recall from section 12 that ArtScran associates view-specific categories with view-invariant categories. The view-specific categories are also potentially sensitive because this ArtScran model top-down expectations are also learned from the view-invariant categories back to the view-sensitive categories. The PRTScan model generalizes this learning to view position and size invariant categories, which can again send top-down priming signals to the view-specific and potentially positionally sensitive categories. These latter categories are computational interface from an invariant category that represents Waldo to a target position for Waldo's current location. ArtScan search was tested by learning to recognize and search for Caltech 101 images of natural objects in the scenes that contain non-overlapping objects, as well as simulated reaction times measured in human search tasks. ArtScan search cannot, however, quantitatively simulate how humans use spatial and object context to learn how efficiently search for objects in a scene, and when seeing a refrigerator and sink leads to a higher expectation of next seeing a stove than a bed, and also where to look for the stove in a familiar kitchen. The ArtScene model and the ArtScene search model illustrate how humans accomplish these goals. ArtScene explains how the gist of a scene can be rapidly learned and recognized as a large-scale texture category. Scene identity can be refined by scanning the scene with attentional shrouds to categorize finer texture categories within it. Recognition performance is then determined by using all the learned texture categories to vote for the best scenic label. The resonance that occurred during such a recognition event is a type of feature category resonance. At the time ArtScene was published, it reduced the error rate of a popular alternative scene classification models by over 16%. ArtScene search goes further by incorporating spatial and object working memories, spatial and subject list chunks, and spatial and object priming signals using interactions within the pararhinal and parahippocampal cortex, prefrontal cortex, intertemporal cortex, and parietal cortex. A sequence-sensitive spatial and object list chunks guide context-sensitive searches using top-down expectation pathways that can support feature category resonances when expected positions and objects are realized. ArtScene search can quantitatively stimulate key psychophysical data from experiments on contextual cueing, including spatial and object cueing, positive and negative spatial cueing, and local and distant cueing effects. Okay. So conscious versus non-conscious emotions. Many experiments have shown that emotional processes can be activated without causing conscious awareness or knowing about them, yet these emotions can nonetheless influence subsequent behaviors. In the current theory, any simulation that does not cause a vigorous and sustained cognitive emotional resonance that includes, but is not restricted to, temporal cortex, amygdala, or prefrontal cortex may lead to non-conscious outcome. It may be due to insufficient sensory simulation in terms of intensity or duration, attention distracting tasks, or any other manipulation that prevents a full resonance from developing and being sustained. In particular, the amygdala and hypothalamus can interact without necessarily leading to conscious awareness. 2010 study reviewed several different kinds of experiment evidence that led to a similar viewpoint, but without mechanisms of adaptive resonance to derive mechanistic conclusions. They write that a major difference between the two types of perception, conscious and non-conscious, may be the combined involvement of cortical areas and of cortical-subcortical interactions when stimuli are consciously perceived. The dichotomy of conscious and non-conscious perception of emotional signals can thus be reformulated in terms as the integration of activity in subcortical and cortical structures, where the amygdala figures prominently in the review of relevant emotional structures. Cognitive emotional resonance in the cognitive motivator models links subcortical structures such as the amygdala and hypothalamus with cortical structures such as the temporal and orbital frontal cortices into a bound state that supports both the feeling of what happens and the knowledge of what events has caused it. Conditioning and consciousness, trace conditioning, hippocampus, and time cells. Need for sufficiently sustained cognitive emotional resonance to generate a conscious emotion is illustrated by trace conditioning experiments in humans. These experiments describe a link between conscious and conditioning, including a role for hippocampus in enabling condition to bridge a temporal gap between CS and subsequent US. Such a temporal gap exists during trace conditioning, during which the conditional stimulus terminates before the universal stimulus, but not delay conditioning, where the CS and US overlap in time. Correspondingly, amnesic patients with hippocampal damage learn at a normal rate during delay conditioning, but not during trace conditioning. Postulate 1998 postulated that normal humans acquire trace conditioning because they intact declarative and episodic memory, and therefore can demonstrate conscious knowledge of a temporal relationship between conditioned and unconditioned and universal stimulus. Trace conditioning requires the acquisition and retention of conscious knowledge and would require the hippocampus and related structures to work conjointly with the neocortex. Various other studies have linked consciousness and conditioning. These theoretical results suggest episodic memory may not necessarily be consciously experienced emotions, may not be necessary to consciously experience emotion. On the other hand, the hippocampus is indeed part of the brain system that supports episodic learning and memory. Both spatial and temporal representations coexist in the hippocampus, and both space and time are recombined in episodic memories. Recent neuromodeling proposes why spatial and temporal representations coexist in the entorhinal hippocampal system by showing how they exploit similar circuit mechanisms to represent the large spaces in time that control spatial and adaptively timed behaviors, a discovery that has been summarized with the phrase neural relativity. The homologous model circuits in the entorhinal hippocampal cortices that represent space and time are called spectral spacing and spectral timing models, respectively. The spectral spacing model shows how entorhinal grid cells, our hippocampal place cells, may be learned and control spatial navigation among other spatial behaviors. The spectral timing circuit shows how adaptive the timed reinforcement learning and motivated behaviors can be achieved. Thus, whereas the spectral timing circuit may help to sustain a cognitive emotional resonance, the full resources of episodic memory may not be needed to support consciousness during trace conditioning, especially in conditioning paradigms where no spatial navigation occurs. Predicted mechanistic homologue between spatial navigation and adaptively timed conditioning circuits in the entorhinal hippocampal system has quantitatively situated challenging data in both domains, but also suggests new testable hypotheses. For example, the ability of spectral timing circuits to bridge long time intervals has been attributed to the metabotropic glutamate receptor system. Does such a biochemical substrate give rise to hippocampal time cells? Does a similar biochemical substrate enable spectral spacing to represent large spaces via entorhinal glia cells? So why Weber law? Distinguishing expected and unexpected disconfirmations. So what is the functional utility of the Weber law property during behavior? Adaptively timed responding is essential for terrestrial animals that actively explore and learn about extended environments, since rewards and other goals are often delayed in time relative to the environmental cues that predict their future occurrence. The spectral timing model accomplishes this by predicting how the brain distinguishes expected disconfirmations, also called expected non-occurrences of reward, which should not be allowed to interfere with acquiring a delayed reward, from unexpected disconfirmations, also called unexpected non-occurrences of reward, which can trigger the usual consequences of predicted failure, including reset of working memory, attention shifts, frustration reaction that can counter condition unsuccessful cognitive emotional associations, and release of exploratory behaviors to find better sources of value goal objects. How does this distinction between expected and unexpected disconfirmations work in practice? Key questions that must be answered to understand this distinction include: what spares an animal from erroneously reacting to expected non-occurrences of reward as predictive failures? Why does an animal not become so frustrated by the immediate non-occurrence of reward that it prematurely shifts its attention focus and releases exploratory behavior aimed at finding the desired reward somewhere else, leading to the relentless exploration for immediate gratification? Alternatively, if the animal does wait, but the reward does not appear at the expected time, then how does the animal then react to the unexpected non-occurrence of the reward by resetting its working memory, shifting its attention, becoming frustrated, and releasing exploratory behavior? The insight is that the process of registering art-like sensory matches is not inhibited during either expected or unexpected non-occurrences within a sensory cognitive art circuit. In either case, if the reward happens to appear earlier than expected, the animal could still perceive it during a cognitive emotional resonance and release a consummatory response rather than directly interfering with the matching process. The effects of mismatches upon reinforcement, attention, and exploration are prevented by inhibiting the oriented system's triangle region with the vigilance parameter P inside of it. In other words, one role of the spectral timing circuit of the hippocampus is to inhibit the art-oriented system in the hippocampus during an expected non-occurrence, and with it, the arousal that would otherwise have led to undesired cognitive, emotive, and motor consequences. Because the spectral timing response begins immediately after its triggering stimulus and builds throughout the interstimulus interval, or ISI, between the conditioned and universal stimulus, it can maintain inhibition of the oriented system until the expected time of occurrence of the reinforcing stimulus. The inhibition would not, however, occur in response to the unexpected non-occurrence because the spectral timing circuit would not be active then. As a result, an unexpected non-occurrence could lead to the usual consequence of cognitive, emotional, and motor responses to correct the predictive error. The Weber law property of hippocampal spectral timing circuit thus realizes three critical functional roles. By beginning right after its inducing stimulus, it can inhibit spurious oriented responses throughout its adaptive time interval. By exciting orbifrontal object value categories, it can also maintain motivated attention upon the correct orbifrontal representations throughout this time interval. Finally, by peaking at the expected time of occurrence of the reinforcing cue, it can generate a peak amplitude of motivated attention at the correct time at the orbifrontal representation that controls learned responses. Effects of hippocampal, amygdala, and orbifrontal lesions of learning and memory. In addition to explaining data about normal delay and trace conditioning, the NSTART model explains why simulates many subtle data about how learning and memory consolidations are induced by different brain lesions. In particular, the model proposes a unified explanation in computer simulations of why lesions of amygdala, hippocampus, and cortex have different effects depending on the phase of learning when they occur. In particular, explains why the hippocampus is typically needed for trace conditioning but not delay conditioning, and what the exceptions reveal why amygdala lesions before or immediately after training accelerate conditioning, while those made later do not, while thalamic or sensory cortical lesions degrade trace conditioning more than delay conditioning, why hippocampal lesions during trace conditioning experiments degrade recent but not temporal remote learning, why orbifrontal cortical lesions degrade temporal remote but not recent or post-lesion learning, why temporal graded amnesia is caused by ablation or prefrontal cortex after memory consolidation, and how neurotrophins, notably brain-derived neurotrophic factor, influence memory formation and consolidation. This unified explanation also overcomes problems of alternative memory consolidation models and incorporates many new testable predictions about how memory consolidation works both in normal individuals and clinical patients. Okay, 20. Section 20. Some other approaches to consciousness. The field of consciousness studies has exploded since the seminal article of Crick and Koch in 1990 in both its own journals and conferences. Crick and Koch described two forms of consciousness, a very vast form linked to iconic memory and a slower one where an additional attentional mechanism transiently binds together all those neurons whose activity relates to the relevant features of a single visual object. This conclusion was consistent with available results about art, but did not offer a linking hypothesis between brain dynamics and perceptual, cognitive, and cognitive emotional representations whose resonance support different conscious qualia. A great deal of additional experimental evidence for neural correlates in consciousness has been reported since 1990, but has typically led to theoretical conclusions that fail to make the critical linking hypothesis between specific dynamic brain representations and specific conscious qualia. For example, the neuroglobal workspace, which builds upon the global workspace, claims that consciousness is global information broadcasting within the cortex to achieve massive sharing of pertinent information throughout the brain. Dehane also makes a number of useful observations, including the time that our conscious vision spends entertaining and interpretation is directly related to its likelihood given sensory evidence received, and that the conditioning paradigm suggests that consciousness has a specific evolutionary role, learning over time rather than simply living in the instant. the system formed by the prefrontal cortex and its interconnected areas, including the hippocampus, may serve the essential role of bridging temporal gaps. Such claims are consistent with the analysis in this article, but they do not describe the underlying organizational principles, neural mechanisms, or brain representations that embody subjective conscious aspects of experience. In particular, the claim about global information broadcasting is consistent with analysis of how adapted resonance, such as surface shroud and feature category resonance, may synchronize the dynamics of multiple brain regions, but does not provide insights into the contents of conscious experience or the different kinds of resonance that support them, as summarized by the table 2. The observation that links conscious vision to likelihood is clarified by properties of the shunting competitive networks wherein winning conscious resonances are chosen, whether at the level of surface shroud or stream shroud resonance or representing individual precepts, or of higher order decisions about the most predictive list categories in a masking field for representing the most likely interpretation of a recent sequence of events and the best prediction for what will happen next. The comment about the role of hippocampal prefrontal interactions during conditioning does not provide insight into how or why spectrally timed learnings occur, notably the distinction between expected and unexpected disconfirmations during terrestrial explorations and learning, or the functional role or neural mechanisms that cause Weber's law of property. Continuing the spirit, Tononi defined the scalar function, the quantity of consciousness available to a system, as a value of complex of elements. So this function is the amount of causality effect of information that can be integrated across the information's weakest link of a subset of elements. So Tononi 2015 goes on to further develop postulates for the integrated information theory for physical systems that include consciousness, such as intrinsic existence, compositionality, information, integration, and exclusion. These postulates summarize some basic facts about consciousness, but do not explain them. For example, the integration postulate claims that each experience is unified and cannot be reduced to independent components, much as an adaptive resonance is a bound state. The exclusion postulate claims that every experience is limited to particular things and not others, and has its own spatial temporal grain, much as resonance develops through time, focus attention on some feature of the combination while inhibiting others, and may be adaptively timed by spectral timing circuits. The information postulate claims that selective past causes and selective future effects are represented, much as a cognitive emotional resonance can discover which combinations of features are predictive and which are accidental and intentionally blocked, and so on. Although these postulates tangentially touch upon some of the themes that the current article discusses, they have not demonstrated an ability to parametrically explain significant psychological and neurobiological databases. The current article provides ample evidence that no scalar valued function can explain the brain principles, neural mechanics, and dynamic events that give rise to specific conscious experience. So both Danani and Tonini use the word information as a critical component of their hypothesis. But what is information? The scientific concept of information in the mathematical sense of information theory requires that a set of states exist whose information can be computed, and that fixed probabilities exist for transitions between these states. In contrast, the brain is a self-organizing system that continually creates new states through development and learning, and whose probability structure is continually changing along with them, without a theory that explains how these states arise and how their transition probabilities may change through time in response to changing environmental statistics and internal representations thereof. The classical concept of information is useless. How such states arise is a key explanatory target of art, and one reason why art can offer classification of the resonances that are proposed to embody specific conscious experience. And its highly cited book called Consciousness Explained, 1991, argued against a Cartesian theater model, a place in the brain where it all comes together and generates subjective judgments. Instead, Dennett advocated a multiple drafts model where discriminations are distributed in space and time across the brain, a concept that without further elaboration is too vague to have explanatory power. To the extent that Dennett supported his claim with a discussion of visual precepts, he has made some serious mistakes. For example, when discussing surface filling in, he claimed the fundamental flaw in the idea of filling in is that it suggests the brain has provided something when in fact the brain is ignoring something. The brain doesn't have to fill in for the blind spot. We don't notice these gaps, but they don't have to be filled in because we're designed not to notice them. In other words, Dennett argues that a physical process of filling in does not occur. Given that Dennett put an example of neon color spreading on the back cover of his book, He clearly viewed this claim as an important part of his proposals about consciousness. His proposal explained no data about how filling in works and what its properties are, despite the fact that he learned about neon color spreading at one of my lectures about brightness and color perception, where many properties of surface filling in were explained, including model simulations of many perceptual data, including data about neon color spreading, that still have no explanation without invoking filling in. Instead of offering explanations, Dennis offers sarcasm. The idea of filling in is common in the thinking of even sophisticated theorists, and it is indeed a dead giveaway to vestigial Cartesian materialism. What is amusing is that those who use the term often know better, but since they find the term irresistible, they cover themselves by putting in scare quotes. In fact, many perceptual neurobiological data support that filling in occurs, and it is fully consistent with the multiple drafts perspective. Various other authors have made interesting comments about consciousness based on properties of perceptual and neurobiological data. Notably are Victor Lamb and his colleagues. However, these contributions have not proposed organizational principles of brain mechanisms whereby to understand the brain dynamics of individual conscious experience, including how they may share similar principles of resonant dynamics, yet also occur in different brain regions where they embody solutions to the environmental constraints that differentiate seeing, hearing, feeling, and knowing. Perhaps the theory of Damasio comes closest to theoretically linking the brain to mind by providing what is in effect a heuristic derivation of Kagan model to explain his clinical data about cognitive emotional interactions, but this theory provided no mechanistic account, could therefore provide no data simulations, and did not situate the heuristic derivation within a larger theory of how brain readiness and consciousness may be linked, including remarks. Unified experience of perceiving, knowing, and feeling. To elaborate the general prediction that all conscious events are resonant events, this article proposes how specific neural circuits and systems in different parts of the brain generate adaptive resonance that support conscious awareness and knowledge about external sensory inputs, such as specific sight and sounds, or internal sensory inputs, such as specific emotions. Each resonance supports an attention or focus upon perceptual or affective representation that becomes conscious and synchronizes with relative attentive resonance that enable conscious recognition or knowing, or the perceptual or affective effect, spatial, object, and motivational attention all play a role in these events. This article also suggests how conscious, perceptual, cognitive, and affective representations can also resonate together so that individuals can consciously know and experience feelings about what they consciously perceive. Each of the resonances that support different kinds of conscious experience occur at the brain interfaces that can trigger control of appropriate actions, notably actions that lead to the closing of the brain, environment, perception, cognition, emotion, action loops. Many psychological and neurobiological data have been explained and predicted using properties of these resonances in both normal, individual, and clinical patients. This article has unified the explanations of many previous treated data, explained additional data for the first time using its newly discovered concepts, and made new testable predictions. Many more data are explained in the original archival articles that introduce various of the synthesized concepts about vision, audition, emotion, and recognition. As such, resonant dynamics unfold through time. They are bound together into a unified sense of self with the help of the coordinated opening of multiple cognitive and motoric gates by the basal ganglia. More modeling work needs to be done to demonstrate this basal ganglia coordination in the spirit of, but moving beyond the simulations of the Least-Telos model. Each resonance may involve multiple brain areas and not all cells within a resonance may support conscious qualia. Only cells that can represent the features that discriminate perceived difference can do so. A conscious experience may not always be triggered even by active cells that can support such discriminations if inputs to a circuit that is capable of resonance are too brief or insufficiently intense, or these inputs unsuccessfully compete for attention across cell populations that are more fully activated. The activated cells can nonetheless offer non-consciously influence future behaviors. Using self-organizing and self-stabilizing expertise to control changing bodies, Art explains how perceptual and cognitive processes in the what ventral processing stream use excitatory matching in match-based learning to learn attentive representations of objects and events in the world. Match-based learning solves the stability-plasticity dilemma and can occur quickly without causing catastrophic forgetting. Much of the new faces can be learned quickly without forcing unselective forgetting of familiar faces. Excitatory matching can also support sustained resonance and thus sometimes conscious awareness when a good enough match will object information occurs. Such mass-based learning supports the creation of category representations at higher cortical levels that are increasingly invariant under changes in the object's view, positions, and sizes when it is registered on our retinas. That is, match-based learning can support invariant categorical learning, which enables learning to categorize the world without causing a combinatorial explosion of memories. However, these properties are not sufficient for a brain to accomplish autonomous adaptation to a changing world, if only because positionally invariant object categorical representations cannot by themselves be used to manipulate objects of a particular position in space. Complementary spatial and motor processes in the Warehouse dorsal cortical processing stream can be used to manipulate objects to space. To do so, they often use RAM-like inhibitory matching and mismatching learning to continue update spatial maps of sensory motor gains as body parameters change through time. These circuits cannot support an adaptive resonance under any condition and thus do not support conscious awareness. Although each type of matching and learning is insufficient on its own to learn about the world and to effectively act upon it, together they can. Perceptual and cognitive processes use excitatory matching and match-based learning to create self-stabilizing representations of objects and events that embody increasing expertise about the world and conscious awareness of it. Complementary spatial and motor processes use inhibitory matching and mismatch learning to continually update spatial maps and sensory motor gains to compensate for bodily changes throughout life. Together, they provide a self-stabilizing perceptual and cognitive front end for conscious awareness and knowledge acquisition, which can intelligently manipulate more labile spatial and motor processes that enable our changing bodies to act effectively upon a changing world. Okay, so the culmination of a lot of research there was this paper. It took me over 2 hours, and I read probably about 80% of it. So I appreciate people who tuned in for this. I have quite a few slides that I want to finish up. Like, this study, I guess it's came kind of unclear to everybody what's going on, where am I headed with this? And really, this was just a review session for me of 20 years of data and study. So, obviously it's going to be hard for just people to follow along. And, so this is more just a public study session. And hopefully after I'm finished with this, I'm going to be able to make better content, but I needed to review my data in order to do that, because, lifetime of learning, I have it on recall and, understanding and put up to date and try to connect this information, as could be seen by, what I just did. So I want to talk, Christianity, and I want to talk Judaism and the soul. So I want to finish up these slides, whatever I can right now on these important philosophical topics. So I have quite a few slides on deconstructionism and linguistics, which are kind of the culmination of this stuff. Extremely complicated science. Linguistics might be, it's like neurobiology, like brain surgery almost, from a theoretical level. And you see how all these different sciences will actually connect to actual, to how the brain operates. And then I'm going to go back into I'm going to do an overview of Christian theology, and then I'm going to, go back to my area of expertise, namely the soul, and Judaism. But I needed to cover all this other data first. And all the people who joined me for quite a few of these, I'm glad you did. I hope you gained from it. And, hope these public study sessions were worthwhile to you. Maybe other people will start doing similar things, and people doing research on these areas will be able to combine our studies and arrive at a broader truth. So I'm just preparing these slides. I want to get this done tonight. So I know the stream's already been long, and I spent so much time reading, over 2 hours reading through that article. And I saw it came down to like 0 people watching, and I appreciate it, understand it's very hard. I don't know if I was someone else, if I'd be watching me, probably I wouldn't. So everyone who did stick through it, I'm glad you did. We take a quick drink, and then we enter back screen share mode. And we're going to finish up. So back screen share mode. Make sure the sound's working. Okay. So let's keep it going. Okay. So Wittgenstein and Heideggar. Talked about Wittgenstein briefly, and we'll move into existentialism to deconstructionism. So between the 20th century, philosophers were struggling with the post-Nietzschean deconstruction of metaphysics. Philosophical deconstruction is a close textual analysis that focuses on uncovering the overcoming privileges hidden in philosophical arguments and theories by taking a text apart. Philosophical deconstruction has its most direct and influential expression in Nietzsche's critique of Western philosophy as just one more historically rooted expression of the will to power. So we had the two approaches to philosophy in the 20th century: analytical philosophy and continental philosophy. Analytical philosophy stresses logic, testable precision, and clarity. Common to the way of appropriate philosophy is the notion that the universe consists of independent atomic entities, material particles, sense data, impressions, and facts. Logical and linguistic analysis are said to be the only proper methods for sorting out philosophical confusion. Philosophical archetype of analytical approach is Ludwig Wittgenstein. Continental philosophy tends to explain things not by reducing them to simple entities, but by understanding them in a broader holistic historic context. This approach includes phenomenology, existentialism, and deconstructionism. And Heidegger will represent this. So Wittgenstein, influential analytical philosopher. You see his dates and area. Studied under Bertrand Russell. And other key figures like economist John Maynard Keynes and mathematician Frank Ramsey, philosopher Moore. At the start of World War I, he joined the Austrian army as prisoner of war, gave up philosophy, and worked as a time as a gardener in a monastery, and then as a school teacher and an architect, and eventually returned to Cambridge, got his PhD, and in the next years worked intensely and rejected many of his former philosophical positions. In 1939, full professor at Cambridge. In 1951, he dies. So analytical philosophers emphasize the need to clear up linguistic confusion to show that most philosophical problems are based upon an abuse of language. Analytical philosophers are very interested in technical issues in language and logic, as opposed to traditional philosophical concerns such as the meaning of life. Early analytical philosophers tended to advocate realism. Realism is the belief that there exists an independent, objective world of accessible things and facts. Philosophy should concern itself with identifying and eliminating mistaken claims about reality. So Wittgenstein's Tractatus is seen as a major example of the linguistic analytical turn of the 20th century philosophy. Tractatus consists of 7 main propositions, and comments on those 7, arranged numerically, attempts to show the underlying structure and language. Basic point is to say what cannot be said about thought, trying to say the unsayable amounts, and trying to say the unthinkable. Wittgenstein argues that the complex propositions of ordinary language are meaningful only if they are analyzable into simpler, ultimately elemental propositions that consist only of names. So Tractatus, Wittgenstein further argues, analysis must end in simple, unanalyzable names that refers to objects. Sentences that cannot be reduced to simple symbols are meaningless. Ultimately, all meaningful sentences fall under the natural sciences. Traditional philosophy problems as such do not exist. Philosophy is ultimately an ethical and therapeutic enterprise that enables us to see the world afresh. So upon reflection, Wittgenstein determined that the Tractatus itself relied on illegitimate metaphysical assumptions. Accordingly, rather than one meaningful language, there are many different languages with many different structures and many different uses, In the Investigations and other writings, Wittgenstein talks about languages as we use it in ordinary life, using such expressions as forms of life, language games, and family resemblance, not as once and for all fixed logical extent relationships, but rather certain kinds of natural human practices. Wittgenstein now thinks of words as tools and sentences as instruments. The structure of language now determines the structure of thought and consequently the structure of experience. So Wittgenstein's turn, fact stating is only one language use. There are countless others and thus countless ways of experiencing the world. Language as used in ordinary life exemplifies certain kinds of natural human practices. When philosophy succeeds, it also gives philosophical problems a rest. According to Wittgenstein's, philosophy is a battle against the bewitchment of our intelligence by means of language. Heidegger. So, to many admirers, Heidegger is seen one of the most important philosophers of the 20th century, although he was a Nazi. Heidegger, 1889 to 1976, grew up in a rural village in Germany, Jesuit high school, thought he was going to become a priest, but had a nervous breakdown and studied philosophy, University of Freiburg, studied under Husserl, who we'll be talking about more. So Heidegger, 1927, Heidegger began teaching University of Marburg, meets Hannah Arendt. Heidegger was a well-known and brilliant teacher, in great part due to the conviction that philosophy cannot be divorced from life. 1927, publishes his famous book, Being in Time, and then joins the Nazi Party. Heidegger has children. In terms of students, Jean-Paul Sartre and Hannah Arendt in existential and phenomenology, Hans Gregor Gadamer in hermeneutics, Jacques Derrida in deconstructionism, Rorty in pragmatism, Boltzmann and Tilak in theology, and Taylor and Chauvel in analytical philosophy. So what is this phenomenology, the science of being? Phenomenology is a method of philosophical analysis first developed by Edmund Husserl and involved an attempt to reveal the essence of human consciousness through the descriptive analysis. Phenomenological developed as a reaction to constructivism and the epistemological notion that all knowledge is a product of the human mind. For Husserl, consciousness is always consciousness of something. So according to Husserl, we do not need to answer the skeptic's challenge as to whether the objects of consciousness ever exist objectively. It is enough for all human purposes that the objects of consciousness exist simply as objects of consciousness. Husserl and Heidegger after him were deeply concerned with a European crisis associated with the spread of relativism, skepticism, and the use of science to objectify psychic life, the life of the spirit, and to reduce spiritual realm to matter. The Heidegger blend of phenomenological ontology and existentialism evolved from studying Husserl's ideas. According to Heidegger, Husserl saw phenomenology as the science of beings, whereas it is more properly understood as the science of being with a capital B. Towards this end, Heidegger attempted to articulate the fundamental condition of uniquely human existence, talks about human being, humanity, and the individual human beings, as well as existing in a uniquely human way, not as a mere object of scientific inquiry. What makes us uniquely human is not detached knowledge, but fundamental concern about our condition. So in Being in Time, Heidegger struggles to articulate what he calls the fundamental ontology of being. Heidegger notes that we can be described from two different levels. One level is the ordinary day-to-day level of fact that Heidegger calls the ontic level. We're unique among beings because our nature and the fact that we exist at all is something we care about, something that matters to us. So indeed, our concern with the deeper meaning of our own existence is part of the very essence, part of who and what we are, reflection of a deeper level of being. Heidegger calls this the ontological level of being. This is the level of our uniquely human way of existing in the world. The essence of being human is that we make choices. We lose the meaning of being in the course of our ontic lives. To be human is to be amazed in the presence of being. The they. Anxiety offers us a way to choose authentic existence or to choose to fall into inauthenticity. When the burdens of human condition prove too much to bear, we often seek inauthentic escape by losing ourselves in the they. When we seek false ontological solace in the they, we descend from empathetic being with others to being with one another. We allow an aggregative average to determine how we live and think. Idle talk, fallenness of Heidegger's term inauthenticity, is a mode of being in which we are lost and dominated by the world. For Heidegger, authenticity means living in and with anxiety in the moody understanding of our determinacy. An authentic individual lives honestly and courageously in the moment, refusing to make excuses and does not rely on groups or intuitions for meaning or purpose. The age of technology. In his analysis of technology, Heidegger says that calculative technological thinking sees everything as standing reserve, a source of energy to be stored to await our beck and call. The way of thinking transforms human beings into beings just there, entities to be used and treated like everything else in the standing reserve. This entrance of technology is a way of looking at the world as raw material to be used. Technology is a frame of mind that we have not chosen and that characterizes and dominates our era. So humanity is a conversation. Conversation for Heidegger is progressively attuned. Communication about being is the language function that makes this possible. Language enables us to be amazed by being. Participants in conversation are not merely exchanging information, but rather attuned to each other and to whatever they're talking about. All conversations are really one conversation, the subject of which ultimately is being. So when we do philosophy, we're like savages, primitive people who hear the expressions of civilized men, putting a false interpretation on them, like to draw the queerest conclusions from it. Perhaps the distinction of this age consists in the fact that dimensions of grace has been closed. Perhaps this is the unique disgrace. Okay. So looks like my roommate just came in, so I think I'm gonna call this stream to a stop and continue later. Hopefully, maybe tonight or tomorrow. Okay, shalom. Thanks, everybody. Appreciate tuning in. Hope to do more.